Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Ladies and gentlemen, welcome back to another live stream. And hold on a second. Okay, back. Alright, let's see. I gotta share the live stream. Alright, let's see. Oopsies, I almost ruined it. I almost lost my keyboard. I literally almost lost my keyboard. Oh my god, that would be funny. Anyways, let's see. I gotta share the live stream with the Zig server too. That would be cool, I guess. Let's see. Project Lemon Juice, hello, how is it going? Welcome to the live stream. Oh my god. Let's go, okay, well, here's Dev Lemon. Okay, well, Dev Lemon, Kodataku, your old videos, the old Kodataku is so funny, the chicken voice. Like I could watch two videos back and back and the voice would sound different in each. Doesn't even sound like the same person. I think I had more than 200 videos. You can watch me grow, but I deleted most of it. 70 videos currently up at the moment. Congrats on 3k. I don't think you had 3k last I checked. Yep, I think just today it became 3k subscribers, so lost history. Lol discount. This what really made me laugh. Thanks for the video, but what is that buzzing sound? Are you recording this in level 2 in the background? Oh my god. I think this was basically from my old, really old videos when I didn't have this computer. I just had a potato laptop, pretty much. And the computer fan was like going crazy, first of all, and second of all, like my background, there was a lot of background sounds, I believe. And Marty Flowers, hello, welcome to the live stream. Let's go part 2304B, the triangulation character development arc. Oh yeah. Alright, so please make sure to actually join into the Discord server so you could join in, have some fun with us. Sometimes I do some gameplays with, what is it called? Mind test with people. I actually launched a dedicated server and we play together. I may do a live stream later on with that. But yeah, you also get to vote on the next live stream. For example, today I asked, do we want to continue Vulkan Zig project, programming QA and Mindtest multiplayer, or trying to mod Mindtest for the first time using Lua? So, well, at the time that I have prepared for the live stream, it was the winner was continue Vulkan Zig project. So here we are. So we're continuing the crazy project. Okay. So yeah, pretty much. When is face reveal? Oh yeah. Well, all right. So I think let's get started. Just gotta sip some coffee there. Is there some questions, by the way, before we start? And so yeah, we have made the previous live stream. Well, where was developing the project once again, but the thing is, I just couldn't figure out how. Like, I tried to ease in without the Vulkan pipelines, so to try to just not overflow you with a lot of information at once. But the problem is I found some problems with synchronization of that thing. And the thing is, that kind of way of doing it, not a lot of people does it. Most people just go with the normal mainstream way, which is just to create a pipeline. So I had a really hard time trying to figure out why that wasn't working. I don't know why that was the case. But either way, I just, like, undo all the changes we have done in the last live stream. Unfortunately, sorry for the inconvenience. But I'm going to keep the live stream because, first of all, most of you just voted to keep it. There you go. And also the fact that there was a lot of amazing learning material there too, although we have scratched all that and we're going to start from the previous live stream. So yeah, pretty much. All right, so yeah, okay. So now we're pretty much going to start creating a pipeline, pretty much. So yeah, we gotta start with the shaders, pretty much. So let's get started, I guess. I'm gonna bring in Vulkan tutorial here. This is a very good tutorial, although I don't really agree with a lot of things on it, but it would be a great thing to go with it. So of course I did go through this tutorial like a lot of times, but anyways. So swap chain image views, yeah, we already have done all that stuff. So pretty much you could go to this website. Let me actually give you the link and you could learn a lot about that stuff. Of course it's using C and it's also not loading function pointers like we do. And it's also using GFW, and it's not caring about Android Surface problem, like cross-platform basically. So yeah, I mean, it's a tutorial after all, so that makes sense. So as you can see, here's the pipeline basically. It's kind of like a conveyor belt, kind of. Like you have the input assembler, the vertex shader, the tessellation, the geometry shader, rasterization, fragment shader, color blending, and finally the frame buffer. The frame buffer is basically it's just a combination of the render pass, which we're gonna see later on, and the image, like the swap chain image. So basically, just when you reach the frame buffer, it basically shows up on your screen at that point, right? So first of all, you get the vertex and index buffer, which basically contains data about the geometry that you want to render. Then it goes through an input assembler that, of course, we're gonna go through all the details later on. But it goes through the assembler, there you go. And the assembler kind of like just prepares some data, like on how to manage the or how to read the vertex and index buffer basically. And then every single vertex goes through a vertex shader. That vertex shader basically takes in the data that we have assembled from the buffers and basically transform it. For example, we could use the vertex shader to transform geometry, to scale it, to rotate it. That's basically kind of like, yeah, that's pretty much it. And then there is the tessellation. The tessellation could, this is kind of like optional. This is not something that you would use in a normal Vulkan project. Especially your first one, but here you go, the tessellation geometry shader. These are optional and we're not going to be doing them in this, at least until we get I guess a cube or something. I don't know, we'll see if we ever need them. So the tessellation could be used, for example, in terrain. Like you could, for example, in let's say KSP Kerbal Space Program, they have like a large earthly terrain kind of thing. And if you want to render all of that with high quality, it's just not gonna work. So what you do, you just use a tessellation shader to basically change the quality or how much triangles you're rendering in the terrain depending on the distance from those vertices and that geometry, etc., etc. And there's also geometry shader, which you could use to actually create like new vertices, kind of. And then you have the rasterization. So after we got all the geometry done, we go to the next stage, which is basically coloring those geometry. And there you go. And then after the rasterize, and as you can see, just black and white. Basically, either the pixel is inside or is outside. And hello, our first supporter and only supporter currently. Welcome to the live stream. Okay. Of course, by supporter I mean the membership program of the channel. So yeah, but of course I do have some other supporters like Marty Flowers and Project Lemon Juice, which are very, very active. And thank you everyone for your support. Okay, so we also have the fragment shader. So after the rasterization, which is basically figuring out is the geometry is inside or outside a pixel in the frame buffer, basically, we figure out, we go through like all of those vertices that we have found to be inside of the geometry, kind of. They go through the fragment shader, and the fragment shader, we could do basically anything we want. We could like color it using a gradient, for example. We could sample from a texture and color it with that, etc., etc. You could do all sorts of things. Basically, a vertex shader kind of transformed the geometry. The fragment shader, it colors the geometry. Of course, this is just a layman definition, but you get the point. And there is the color blending, because you may have multiple fragments on top of each other of multiple geometry that are kind of intersecting. Now, at that point, you need to figure out which fragment should be seen on the user screen that will actually be drawn into the frame buffer. And that's the job of the color blending. Although this is not a programmable stage, it is a fixed stage, while fragment shader, geometry shader, tessellation, vertex shader, like you can see that they have a different color. You know, these guys and this guy are programmable, meaning that we could write code, actual code, shader code, to do whatever we want basically in those stages. But in terms of rasterization, color blending, and input assembler, we just have some options to tweak basically, and the rest is done by either the GPU's hardware or driver or whatever. So yeah, pretty much. Okay, so you could go ahead, read through all of this later on. But anyways, so the next stage is the shader modules. All right, so as you can see, we have the frame buffer coordinates. Let's go from 0, 0 to 90, 20, 1080 basically. that's basically a swap chain image. You can kind of think about it like that. So these are the frame buffer coordinates, meaning the actual, swap chain image buffer kind of thing, right? But then there's the normalized device coordinates, which basically goes from -1 to 1 1 basically, as you can see. And of course the center is 0 0. Anyway, so as you can see, you have the vertex 0, vertex 1, vertex 2. And yeah, the order of the vertices matter. So as you can see here, in this case, they're using clockwise ordering of the vertices. Why it matters? Because depending on the order, the triangle will be facing either this side or the other side, either this user or the other side. And you could choose on your own which ordering is the front side, or you could even go ahead and basically show both faces, so you don't even care about that. Now at that point the ordering doesn't matter, pretty much. Hopefully that makes sense. If you have any questions, let me know. Right, so we have here, this is the shader we're going to be doing. So it's currently we're not going to be doing a buffer, because to actually create a buffer we have to go through a lot of other crazy stuff, Vulkan how it is. But currently we're just going to embed the vertices into the shader itself, which is not very scalable and not what you typically will do in an actual project. But this is a good starting point, so you don't have to actually create all the boilerplate for a buffer, etc, etc. But we can be doing it later on. But for now, we're just going to embed it into the source code directly. Now here you can see that we have a version. Of course, this is indicating to the SPIR-V compiler, which is going to be compiling our shader source code into SPIR-V format, which is a binary format that all vendors kind of just agreed upon. It's kind of like assembly basically, but for GPUs in some sense. But anyways, so we have here a function, and you can see that it's kind of like C style kind of language, but it's not C, it's called GLSL. But anyway, there's a lot of languages that you could use, and at the end of the day you could just translate it to SPIR-V and then load it in your program in Vulkan. Now here we have, as I said, a function called main. You could call it whatever you want. You'll see that we can actually tell Vulkan what is the entry point to our shader later on. And then here you have GL position. Now this is an actual global variable basically. You set it here, they're setting it to vector4. Well, a GL position is of type vector4. Here the first, actually the two first coordinates are coming in from the positions array, which is this guy right here. It's a array of vector 2s. And how I knew just from here that is vector 2s, just from the fact that there is 2 values after it. And now basically there is something called swizzling in Vulkan kind of thing, in GLSL I mean, is the fact that, for example, you could make a vector 4 out of a vector 2 and 2 values, or you could, for example, vector 4 out of 2 vector 2s. You could go with out of 4 values, etc. You could do all sorts of craziness. But anyways, here we also have another global variable which is called GL vertex index, and this would be basically passed to us, and it will be the actual vertex index. So it would get, for example, for this vertex, when we're processing through this vertex, we will get 0 for that GL vertex index, and then after that we'll get 1, and after that we'll get 2. Now basically this function will run in parallel, like at the same time on all the vertices of your geometry. Okay, that's why we usually use mathematics to actually figure out how we want to place the geometry or how we want to transform it, because in mathematics you do not have to care about the other vertices. You just You just too simply get some values, like for example, you get an index of a simple number, and then you transform it to a vector 4 in this case, for example, somehow. And that's how you do it, too simply. So yeah, that's pretty much it. So this kind of function will basically kind of like a for loop through all the vertices, and then it will run through this, but it will change this GL vertex index dependent on the vertex kind of thing. So hopefully that makes a little bit of sense. It did take me a lot of time to figure out when I first started, but let's go. Fragment shader. Now fragment shader also it have an entry point. In this case it's called main. You can call it whatever you want, as I said again. And here we have the version. Now the same kind of story with this guy. This fragment shader will run on every single fragment, but just in layman terms, in every pixel. Basically, although it's very different kind of fragments and pixel are different because of the fact that if you remember that we could have like two triangles, for example, that are intersecting. So in one pixel, you could have two fragments, and then you have to do the blending with those two fragments. But just for the sake of simplicity, let's assume that there's no intersection between the triangles that we're rendering. So you could say that it is a pixel instead of a fragment. But yeah, you got the point, hopefully. Either way, as you can see here, out color is actually a global variable that we're setting here, and that we're setting for every single fragment or for every single pixel. In this case, there's nothing really weird. It's just setting it to a constant value. And this is, by the way, RGBA, and every component goes from 0 to 1, where 0 is kind of like black, no color, no light, and then 1, which is like full light, like white, basically. In this case, it's setting R to 1 and the other guys to 0. These are green and blue, but red is full on. And this is the alpha, which is, I think, alpha or opacity. Yeah, I think alpha, which is also full on, which means that the color will be opaque, fully opaque. Although if you want to support transparency, you have to do some fiddling with the blending stage that we talked about earlier between the fragments. But yeah, we'll see how that goes later on. Okay, so we got that out of the way, hopefully. So basically, we're just setting the output color to a red color, an opaque red color. And as you can see here, they're declaring an output variable, right? It's called out color. You can call it whatever you want, but of course you have to, just be consistent. Okay, so vector 4, it's an output, and the location is 0. Now, basically, you could bind to your, how many bits in each float? It's usually 32-bit. I think if you want to use 64-bit, I think you have to actually go ahead when you're creating your device. You have to include a feature. Yeah, you have to enable a feature if it does exist in the GPU. So Vulkan doesn't guarantee that the GPU that you're using would actually support 64-bit floats. Usually in graphics we just use FT32 because usually most applications of graphics like 32-bit for a float is far more than enough. So 32 by default, some 64 not. Yeah, 64 could exist, it could not exist, depends. You have to actually query from Vulkan to see if the driver or the actual hardware does support float 64s. But yeah, hopefully that makes sense. Now here you can notice that we're saying location equals 0 layout. What does that mean? That later on you're going to see that we're going to actually bind to our shaders. Of course, I'm kind of simplifying a bit here, but just bear with me. So we're just going to bind the shader with frame buffers, with multiple frame, well, we could go with multiple frame buffers, but in our case, we're just going to go with one frame buffer, which is going to be out of the swap chain image. Okay, so basically we're going to have one frame buffer, which means one output that we're going to use. So there's only 0, which is the first frame buffer that we're gonna bind, and the only one. If let's say we're gonna need a second frame buffer that we want to output to, then we could basically bind another frame buffer other than the one that we already have here, and then maybe, for example, give it the location 1 instead. So it's kind of like index 0, 1, 2, 3, 4, etc. Okay, nice. So pretty much, hopefully that makes sense. Per vertex colors, making the entire triangle red is not very interesting. Wouldn't something like the phone look a lot nicer? Okay, V0, V1, V2, let's go. Okay. Now, as you can see, they made another array called colors with 3 elements, 3 vectors. And you can notice here that red, this is color red, this is color green, this is color blue. So basically the first vertex will be red, there you go. Second vertex will be green, there you go. And the third vertex will be blue. And just to reiterate, it is that way because the red light is fully on, the green and the blue light are off, so you get red light. Here you only got the green light on and the others are powered off, so well, you get green too simply. And of course you can mix and match with the colors. For example, you could mix full red with full green, you'll get yellow, etc, etc, whatever. Or you could mix all the colors, like all the lights, fully red, fully green, fully blue, and you get white. If you said 0, 0, 0, which means no light is on, and yeah, you get no color, no light, no, well, it's gotta be darkness. So darkness is, or black is just the absence of light basically. So that makes total sense, I guess. Although that's not like fully correct though in an actual screen, because even like in a typical screen, even a black is an actual color. It's not like, it's not fully black, there's still light, but you know, there's just some crystals there that making it look black. But your battery is still draining on that black pixels. But then there is some new screens, I don't remember the name though of those screens. Let's see, let me try to find the name. What they're called, OLED, exactly, OLED. So there's OLED screens that actually have true blackness, exactly, OLED. So those, actually when you have a black, that means total absence of light, and that's why those screens, you can really see the contrast, and the image looks just much nicer. And also you get to let's see, to economize on your battery life, etc. But anyway, no background light, exactly. Okay, so next we need to add the matching input in the fragment. Okay, as you can see here, they have set the frag color. Now here they're doing this in the vertex. Notice that they're doing this in the vertex. They have included another variable inside of the vertex shader called frag color, and they bound it to location 0. And here for every single vertex, now pay attention, for every single vertex, not fragments, for every single vertex, we're setting that frag color output to colors, which is our array with the index GL vertex index, the same one that we have used before. But then in our fragment shader, what we're doing, we're coming here, we're creating an input variable called frag color. This is the fragment shader, and we're setting the out color that we've seen before to vector4 frag color. And remember that frag color is vec3, and vec3 plus one component is, well, vec4. So, and here we're setting the alpha to just 1.0. It's basically constant. But this, we will get it as an input. Input from who? From the vertex shader. Because here, notice that here in the vertex shader, we have made an output variable. And then here we have made an input variable. And I know that this guy is the same as this guy. Why? Because they have the same location, location equal to 0. So when you have an output and a corresponding input with the same location in the vertex shader and the fragment shader, then you know those, basically the vertex shader will actually pass in some data to the fragment shader. Of course, there's also some other process that happens that makes it look gradient, because, well, what we're doing here, for every vertex, we're going to pass to the fragment shader one color, which is going to be, in this case, red, like blue, and then green. But the thing is, how did we got a gradient? And that's a fact, because fragment shaders kind of does, like, what is it called? I don't remember. Let's see if we can find it here. Yeah, interpolation. Okay. Fragment shaders does interpolation between those vertices colors, and that's why you get these kind of gradients, basically. Although you only set the colors of the vertices themselves. So, of course, you can actually go ahead and, disable those that interpolation, and you'll get something called flat. I don't really remember, but hold on a second. Flat. Let's see if I can find it. No. GLSL flat color, I guess. Flat shading, maybe. Hold on. Hopefully I can find it. Well. Okay. I guess this is, although not the best example, but I think this should do it. There you go. Open image in new tab. Okay, so here there is no blending, there's no interpolation. As you can see, every quad is actually flat shaded, which means there is no interpolation between the vertices, I think. Although this is not the best example that I wanted to show, but yeah. Hopefully that got the point across. But anyways, so let's see what else. Now we have finished with that stuff. Now compiling the actual shaders. Okay, now this is the actual full vertex shader, and this is the full fragment shader. And then here we'll use, you have to actually install the, what is it called? The Vulkan SDK. And you'll find there an executable called glslc, .exe, or you could also use another compiler, but yeah, anyways. And then you just pass it the file name and then the output file name if you want to, and then it will give, like, it will take your source code and basically compile it down to SPIR-V binary code, kind of. Hopefully that makes sense. Now you would notice that, let's see. Well, anyway, never mind. We're gonna come back to it later. Anyways, let's see what else. You could also use a library called libshaderc to actually compile your source code in the fly, and that's kind of similar to how OpenGL does it. Like, your application just have the source code, and then you just, the driver goes ahead and compiles it in real time. So you can see how really slow that is. And it's not just slow, but also there's the problem that every single vendor, like NVIDIA, Intel, what else, AMD, all of these vendors have to actually create the compiler themselves, their own compiler. And some vendors would implement the compiler in some way and the other in some other way. For example, one implementation could be a little forgiving, the other could be more strict to the specs to the specification. And so what you end up with is that your same OpenGL code actually either doesn't work on some platform or something like that. Like your code doesn't work on some vendor, but it works on another, or maybe the visuals are different. So that's a big problem in OpenGL. But in Vulkan, you actually do the compilation yourself. You just give the driver your binary. Of course, that binary that you get of SPIR-V is not really the final binary that will actually get run in the GPU. But you know, it's kind of like just kind of like LLVM IR, which is like what is it even called? Hold on, let me see. IR, LLVM IR. What is it called? I just remembered I think intermediate. Yeah, intermediate representation, basically. That's kind of like an intermediate representation. Exactly, intermediate representation. And then the driver actually, instead of taking the whole source code and building a whole compiler for it to their own bytecode or assembly or whatever of the GPU, they just take your simple SPIR-V assembly and they turn it to their own implementation dependent or GPU dependent assembly, kind of. So with that out of the way, you got more consistent, like you're sure that your code would actually run fine with like all the vendors, hopefully. Okay, let's see like WebAssembly for GPUs. What do you mean by WebAssembly for GPUs? Bytecode, yeah, it's bytecode. SPIR-V is bytecode, right? Nice, yeah. Okay, well, WebAssembly is kind of a different thing by itself. Well, SPIR-V and WebAssembly are both kind of like, you know, like basically assembly languages in some sense, bytecode. But anyways, all right, let's see what else, where we are. Okay, right here, they're using C++, of course, to load the shader. We don't have to, to explain that. SIG-G, read, whatever, okay. Create graphics pipeline, there you go, they're reading the files. They're actually loading the SPIR-V code. And by the way, there's another advantage of doing this rather than the OpenGL way, which is basically embedding the actual source code with your binary, which is the fact that people will have a harder time figuring out what your shaders does. Because, well, when you have the actual source code in your program, so you can feed it to the driver at runtime with OpenGL, for example, like anyone could just read through your binary and they will find the string, like raw string of the shader, so they could easily just take it out. But when you actually compile it beforehand and just include the SPIR-V, while of course they could reverse engineer it, but of course it's gonna take a lot much. It's gonna need some knowledge and it's a bit harder, you know. So hopefully that makes sense. So it also makes it harder for people to copy your work, basically. Okay, nice. Creating shader modules. So we're reading the files. With Zig, we could just use embed, so we do not have to do this at runtime. We could just embed it into our executable or our binary at compile time. Although this have advantages and disadvantages though. If you embed your source code at compile time, what's going to happen is that every time you change the code, every time you change the shaders, you have to recompile your whole program, or at least the stuff that is involved, the source code that is involved. But when you actually load the shaders at runtime, it's just like a scripting language. You could change the shaders like after you can even compile the program, and you don't have to recompile your program to actually see the shaders change, you know, like basically. So, but the other problem with this is that you have to make sure that you're reading the files and you're embedding the files in a really cross-platform way, and that's very hard. Yeah, especially with Mac, I guess. I'm not sure about that, but at least, for example, for Android, you have to do some weird, crazy stuff there to actually make it work, because you have to deal with the API of Android, I think, or something like that. But anyways, vacate create shader module. Okay, fine. So here it's too simple. Code.size. We're gonna come to it. We're gonna do it later on. Okay. All right, we create modules, shader stage creation. All right, so right now we'll get to code. Hopefully it makes sense. Is there any questions? Now we'll get to the actual code. Okay, let's see. So, well, let's actually create the shaders first. All right, let's see how we can do that. Okay, I'm going to create, I think, a dev folder kind of, or assets, dev assets maybe. You could call it whichever you want. Okay, dev assets, and then let's say, for example, we could have our vertex shader, our vertex, or just shader.vert, right? And then shader.frag. So basically fragment and vertex shader. Okay, and let's just go ahead and copy the code so we don't waste time that we have here. So shader.vert, there you go. Let's go. And yeah, you could probably find some extensions for GLSL. There you go. I think I have open. Yeah, I have WebGPU stuff on, so let me actually reload my thing and then let me install GLSL instead. Okay, let's see if that helps. Alright, also telling me some syntax error, but I think that's just probably a false positive, or I don't know what it is that, but anyways, we'll see how it goes. Expected an operator between the two operand. Well, honestly, you know what? Just disable it. Who cares? Reload. I'll see about that later on. Anyways, so that's the vertex shader. Now let's get the fragment shader. And there you go. Where's fragment? There you go. Nice, nice, nice. Now we gotta compile these up. Now, if you're on Arch Linux like me, you can just install the Vulkan Devil Arch package, which contains all the stuff you need, like basically all the Vulkan SDK. You got the SPIR-V tools, all these packages included in one group. It's called Vulkan Devil. And then there is, of course, Devil stands for development. And then there's also, if you are on Windows, you gotta install, of course, the Vulkan SDK. I think I've already shown this, but just for the sake of completeness, so no one is confused. There you go. You go here, you download the Vulkan SDK. Let's see, and you just click on which platform you are. As I said, if you are on Linux, you probably will find the Vulkan SDK on your package manager anyways. So, but if you're on Mac, Android, Windows, there you go. All right, anyways, so that's pretty much it for those ones. Now, since I have the Vulkan SDK, I have GLSLC. There you go, no input files. So now I could just say GLSLC. Sorry. Okay. GLSLC dev assets slash shader dot frag, and then you say -o, and then you say where you want to put it. In my case, I'm going to create another folder inside SRC called, I guess, assets. Again, you can call it whichever you want. You can structure your program however you want. And here I'm just going to say src slash assets slash shader frag .spv, or I could just say maybe shader.frag.spv, for example. And there you go. We have compiled it. Now we got the SPIR-V code. Let me see if I can get some hex or something like that. some hex editor. Let me see if I can use that now. There you go. We got the hex, and you can see that there is some actual strings there, like GL Google, CPP, style line directive. Because by the way, this GLSLC is actually made by Google, so that's why it's there. And there you go, the actual variable names. But the variable names I think are included because it's probably like the actual debug information is probably enabled by default, I think, but you could probably change that, and so you won't see any of this crazy stuff. But anyways, now let's go ahead and compile the vertex shader. So vert, and there you go. Now we got both the SPIR-V of the frag and the SPIR-V of the vertex. Now to the actual Vulkan code to actually load in our stuff. Now in Zig, just for the sake of simplicity, I'm just going to actually embed the shader bytecode into my own program instead of loading it at runtime, and it's quite easy in Zig. So const, you can say shader frag equal to embed file, and then you give it the comp time path. Comp time meaning that this path should be available at compile time. So path is equal in our case to assets, I believe, slash shader dot frag. Let's go. Now we're gonna do the same thing for the other guy, which is shader vert. Yes, there you go. Nice, nice, nice. I don't think the name matters, by the way. The extension also probably doesn't matter, but yeah, you could name it however you want, I guess. Right. Great, great, great. Now we gotta load some functions in, and of course not instance though, we gotta load them in the device. There you go. And honestly, I should probably take these variables like near the place where I use them, but anyway. So const device is equal to a struct. Okay, cool. Now here, let's actually look for the stuff that we need. We're gonna need pfn vk create shader module. There you go. Now we have loaded hopefully our function that would create the shader module. And finally, of course, every time you create something, you have to destroy. That's just the cycle of life. So vk destroy shader module. Okay, let's go. All right. Other than that, okay, so I think this is all we need for now, although we probably won't use this destroy yet, because you shouldn't destroy those modules until you actually created the pipeline itself from those modules. So basically until you're done with them. But anyways, so it will be some time before we can be able to do that. But let's see. Okay, let's go. I would recommend starting the pipeline as soon as possible, but although probably after the swap chain though. So basically, well, I'm going to do it here. Okay. Why I recommend doing the textures and the pipelines as soon as possible, because later on you could basically spin up some threads and kind of like just compile those pipelines and transfer those textures while you're actually preparing the other stuff for your program. But yeah, anyways, so what we do now, let's see, we gotta say const shader, well, shader frag, I guess, is, well, what I'm doing. Honestly, let me actually bring in these guys near me, near the place where I'm using them. Hopefully, we'll see how that goes. Oh yeah, I need the train to actually. Okay, let's go. All right, so we got the shader vert and shader frag. Now let's actually create some c.vk shader module create info, I think. There you go. And first of all, we need the s type is equal to c dot let's see, shader, well, vk structure type shader module create info. There you go. Next up, we're gonna need the code size, and the code size is basically, I believe, how much bytes inside of that. Let me make sure that I'm doing it right. Let's search for it. In, where is it? Vulkan, there you go. Always check out the documentation. All right, code size is the size in bytes of the code pointed to by pcode. Nice. Now the thing is about shader frag, about embed file, it actually, yeah, it gives us bytes, so that's nice. So we could too simply say size of, I guess, size of shader vert, or maybe you could just say shader vert dot len, maybe. I don't really remember, but we'll see how it goes. So there you go. Const shader vert info, and what else? The p code. P code is actually equal to, well, shader vert. I think, is that an array, right? Yeah, that is an array. Okay, great. So you gotta do it like this. And then pcode, pnext, s-type, flags. Now we could go pnext. Honestly, I may change all of those 0 init to just regular structs, honestly. I don't know, but probably, because it can be quite confusing, because sometimes it may you know, like miss some fields, some important fields, and you don't know what's going on. So I'd rather anyways just do it. So pnext, pcode, flags is type. All right, cool. What else? There's also flags, right? Flags, I don't think there's any interesting flags here, so just 0. Now pretty much same thing with the other guy. Shader frag info, and now instead of shader vert, we're gonna go with shader frag, and there you go. Now since we got the infos, now we could actually go ahead and say vk map, well, map vk error, try, oopsies, try. And then here we could actually say device.dispatch. Let's see, create shader module, and then here, let's see what we give it. I think we give it the device, we give it the create info, allocation, callbacks, and shader module. Okay, great. Create shader, oopsies, well, where is it? There you go. Okay, so first of all, device.handle, and then you need the, I believe, the info, shader vert info, and then you need the, let's see, allocation callbacks probably, which is gonna be null in here, I guess. And then it would give us the actual shader module, shader vert module. Yeah, I'll surely abstract these later on, but right now let's just try to make it work. Const, it's c.vk shader module handle is equal undefined, and there, well, actually it should be var, right? And pretty much we're gonna do the same thing, I believe, but with fragments. And if you're like me, you're probably itching to actually abstract this out. Let's see, frag, shader, frag. Okay. But I find it much more productive and much easier to debug to first of all trying to make it work than actually abstract it. Okay, so I think we're good to go. Let's try to zig build run. Okay, so expected type cconst u32 found const this guy. Interesting. So let's actually try to ptr cast that, I guess. Let's see. Oh, it actually needs the u32. Interesting. I probably need also a line cast. Not sure though. I probably can look it up. Hold on. So same thing with this guy, I believe. Let's see. And there you go. But I think we have a problem. Invalid SPIR-V magic number. Interesting. So maybe I have a problem with the actual alignment, as I said before. So I'm going to really cut time and just look up vulkan zig binding. There is a great example there, and maybe we can get a hint there about how to do alignment. Let's see examples. Come on. Shaders, graphics, context. I don't remember where it was. Probably here. Create shader. There you go. Create shader module. And as you can see, they're doing it like this, as const u32. But I don't think that would fix the problem, though. Yeah, I don't think. Well, I guess let's check it out. And by the way, how they're doing it? They're doing it by having the shaders here. Yeah, they're having the shaders there, and then they also have, well, what? Shaders. Where is the actual compiled shaders? Let's see. Create shader module. And there is const shaders there. Oopsies, const. They're importing shaders. Oh, I just remembered. This binding have actually a custom step to actually compile shaders in. So yeah, I guess that makes sense. But anyway, let's just try the way they're doing it. Well, let's see. PTR cast. Let's see if that fixes the problem. Hello, Travis. Welcome to the live stream. How is it going? Welcome back. Let's see. As let's go and let's try the other one. Or maybe I miscalculated something. Hold on a second. Maybe I mismatched something. So there's shader vert info. It's shader vert.len shader frag. Yeah, I think. Anyways, don't you need to do const text align equal 4 equal embed file? I mean, possibly. I quite suck at alignment, but yeah, I think so. I mean, let me check the documentation real quick here. It's not really saying anything about alignment. What about here? Ooh. When you perform a cast like this, you also need to ensure that the data satisfies the alignment requirements of UN32. There you go. Lucky for us, the data is stored in an std vector. Okay, so I think maybe Travis have saved us just at the right time. Okay, let's see if that was the problem. Let's see, where is it? Oh yeah, I actually put it here. What? Embed, there you go. So what it was, a line 4. I did a search for a line in Vulkan Zig and came across some examples. Yeah. Const text align 4. Do you mean like this? Interesting. I did see such code before, but I cannot really remember where exactly. Oh yeah, well, it's still saying invalid SPIR-V magic number, interestingly. Interesting. Maybe you should just try to use a runtime, like getting it at runtime. Maybe embed file is doing something wrong there. How about align of embed alignment 2? Yeah. Let's see. Align of U32. Where exactly should we do that? Where we're embedding. Okay. So align of U32. Let's see. Didn't we fix it last time? But I guess we had some UB it last time. But yeah. Okay, let me have a look into maybe our old stuff, because I think we kind of figured it out. Maybe. Let's see. See my old projects. Vulkan. Zig. Oopsies. Let me remove this guy. Okay, let's check this guy and this guy. And let's see. src, c imports. So here we're just embedding the file and we're using that shader. And we're just doing a line cast 4 there. Interesting. Well, I guess let's try this out. Where? PTR cast. Okay, let's see. Shader vert. Oh, what the? Oh, because Zig have changed something. Hold on. So align PTR cast, then align cast. Yeah. I gotcha. So right now I just need the align cast there, I believe. Although not sure if this would solve the problem. Let's see. PTR. Let's see. Still same problem. Now we can't even know if it's a bug in the actual implementation or what. But I think I have a little idea. Let's go back to what we had before. And by the way, let's just do this. And I think I have a little idea to hopefully fix it. We could too simply maybe see what these guys are doing. Let's see. Git clone because they're basically generating the thing at like using build.zig, I think. But let's see. Git clone vulkan zig. Okay, nice. Now let's actually go ahead and say zig build initialize the build zig temp. Oh yeah, vulkan zig. Let's go. Zig build. C import failed. GFW. Oh yeah, I don't have GFW in my system. Gotta install it real quick. Hold on a second. GFW X11, I think. Yeah, there you go. Let's see, install, apply. And let's go. Okay, I think right now I installed it. There you go. Now we have build those. Let's see. CD. Zig dash shout, isn't it? CD bin. Generator and triangle. Let's try triangle just to make sure this is actually working. As you can see, their thing is working. So, okay, let's see now what they are actually doing. Let's search for, well, find dash uname. I don't remember the command exactly though, but I think it's basically something like this. And known you predict, probably name though, dash name. Let me see. The find command. All right, Linux find command. Come on. Dash name. Didn't I do dash name? Weird. Oh well, let me try it again, I guess. Hold on, let me go actually back first of all. Now let me try to find it. Oh, maybe I have to do this. Oh. Remove the sign, makes sense. There you go. But I couldn't find the shaders though, interestingly. Let me launch code here. Okay. And they have here build.zig. They have also examples. Triangle.zig, and they also have, what is it called? Shaders. Well, create shader module. And there you go. They have shaders right here. They're importing shaders. Okay, interesting. So let me say find dot dash name shaders. Okay, it's inside of zig cache. Cool. And there you go. There you go. And let's go. All right, so this is what it is. Align pub const, first of all. Align of U32. Oh, and they also saying this guy. Interesting. And these are the actual compiled things, basically. Okay, cool. Now, what if I actually try to do the same exact thing that they're doing here, which is quite weird, but okay. The trailing, maybe the key. Ooh, interesting. Okay, let's see. Embed file. What if I've done this and then this? I may also need pubconst. I don't know. Let's see. Ooh, okay. Let's go. And we got saved. All right. Thank God. Oh, well. That was very weird. Okay. But I don't really know. Does anyone knows like why we had to do that stupid thing? Oh, well, it's basically I think an address. Okay. Well, it's an address. We didn't actually get the array itself, but the address. Okay, well, what if I remove this guy instead? Basically, I was taking a reference to my reference. Const u8 has alignment 1. Const has alignment 4. Use align cast. Well, yeah, you have to do it that way for the align to work, seems like. So yeah, there you go. We got it working. Let's go. Amazing. Perfect. 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 Okay, so we pretty much have compiled our shaders, and I don't trust Zig debug mode because last time it really you know, tricked me. But let me try now released, and let's make sure we don't have a UB or some stupid thing like that. Because the quicker you can catch it, the better. So yeah, and it seems like it's working. So yeah, there you go. We have fixed it, and I think this was probably the missing key also in my previous projects where I have undefined behavior, but at that point I wasn't really paying too much attention to release mode, but I don't know honestly, but either way, whatever. So yeah, we're good to go. Now we have the shaders. Now let's go to the next stage. Okay, or should we first of all try to basically kind of, you know, try to abstract it away. Okay, so const shader equal to struct fn init, and then, well, again, const self. I should probably make a shortcut for this kind of boilerplate, but yeah, dinit void and self void. I don't remember what those shortcuts are called. Do anyone remember what those shortcuts are called in Visual Studio? Let's see. Let me try to find them. They have some sort of name. I forgot. Google shortcut. No, I don't think they're called shortcuts. They're called something else. Oh, hold on. If I search for snippets, exactly, that's what I'm looking for. Snippet maker or snippet, something like that. No, I mean snippets. Snippet kind of maker. There was some. There you go. Let's go. Okay. So I don't remember which extension I used in the past though, but I guess I'm going to go with maybe this one. This looks familiar a bit, but don't remember exactly which one I used. All right, let's try this one, I guess. Because that could save us a lot of time from boilerplate code. Vulkan is filled with boilerplate. So let's see. Easy or snippet. What did it do? Control Shift P. Create code snippet. All right, cool. So configure user snippets, fill file with snippet, insert snippet. Cool. All right, let me try to make this work. If I remember well, you do something like this, I guess. And then I usually just create my own snippets. I don't think you need an extension for that. I remember that this extension made it much easier to do it. Or one of the extensions there. I don't remember the exact name, but hopefully this is the one. Let's see. The init self. Yeah, I think pretty much that's it, really. Init. Yeah, let's try this one. Okay. And let's try to create a snippet now using that guy. Create code snippet, and it's Zig. Let's go. Enter snippet name. I don't know. Zig struct, I guess. Zig struct. Yes, zig struct. And enter snippet prefix. I don't know. No. What should I call it? Let's call it class though. Let's call it class and see. Enter snippet description. Who cares? Blah blah blah. Pretty good description there. And let's try it out. And there you go. Let's go. Yeah, without it you end up editing JSON. Yeah, that's what I remembered. It was very, very painful to actually do it without an extension. But there you go. Right now I don't have to make this boilerplate anymore. You just say class and it does the job. So you just say this class now, then you call this shader. And there you go. Amazing. Now I don't have to type that stuff anymore. Lovely. Okay. So init self, the init self void array. Now what's up? Let's get those stuff in. Where is it? Okay, we're going to probably get one of these guys and one of these guys. Kind of something like this. And I'm just gonna grab these, and I'm going to remember the actual type of this. Well, it's basically const in. I could probably take a slice of U8 basically. So yeah, let's go back to the shader struct. Let's go. Now this is what we got. I'm cringing because now you'll have const self is equal this everywhere. What do you think? What should be better? Using it directly or what? Let me know. Right, let's see. Next, flags, code size. All right, so right now let's get the actual data or code. Just use the name of the struct shader in this case. What I like about this way is that you don't have to actually like if you change the name of the struct, you don't have to change it everywhere you have used that name basically. That's why I'm using it. But anyway, so here let's call it code, I guess, and then it would be a slice of U8s, I believe. And then I could just say shader or code.len and then code.ptr. Okay, great. Map vacay error, use of in the colored identifier device. I'm not sure if it's a good idea to do the ptr cast inside or let the caller do that. Not sure, honestly. Well, I should probably. What do you think? What do you think? Let me know. Should I let the caller do the cast, or should I cast inside of the abstraction? We also need the device, and in fact, honestly, instead of doing this here, I could probably make a inside in this case. All right, cool. So I think I'll probably honestly make a factory function instead. Really, I think that may be better. I always find it hard to choose between factory functions and initializers, but I kinda trying to use these guys instead more. So, but let me know if you have any idea on how to choose between them. I do have some ideas, but I don't know. Like, if I go with my ideas, I'll probably never use an initializer. Always just factory functions. Unless in some really rare cases. So, anyways, so, well. Here what we need, fn create shader, right? Yeah. Fn create shader module, and here you get the code, which is gonna be a slice of U8s, Oopsies, what? And here, oh yeah, here you would get either shader or there you go, stuff like that. And then you, well, you don't need allocation callbacks in this case, I guess. Oh, you do, right. Well, okay, self dot device. Oh, actually self, right. Self, well, we need self. Let's go. And then here we got self.device.handle. And then here allocation callbacks. Let's go. Code c dot vacate allocation callbacks. Let's go. And there you go. Lovely. And I don't need to call it shader vert and stuff like that. I didn't understand. Can you explain how using const self this saves you time again? Something about renaming it? Yes, basically. Let's say for example, I want to change the name. Init DNet is more OOP and factories are more C-ish, more of a preference, I would say. There is some advantages to both though, but mostly for factories. Honestly, there's no advantage of OOP over like initializer over. Yeah, there's just some places where you just cannot use factories anyway. But anyway, I think that's probably a video for another time. But anyways, let's see. So for example, if I somehow wanted to change, let's say, the name of this struct, let's say, and I'm using the struct itself inside of it a lot. Now, if I want to change the name, I could just easily change it, you know, to whatever I want. Like, let's say here, for example, I could easily change to shader module. Now, I don't have to change anywhere where I actually have done that. But imagine if I had like a lot of places where I'm actually using self. For example, in device, I'm using self a lot. So if I ever decide to, for whatever reason, rename device to something else, then I'd have to change the name on every single place I actually said device, instead of just making it self, and whenever I want to change the name of something, I could just go ahead, change the name, and that's it. Exactly, yeah, pretty much. Hopefully that makes sense. Alright, so shader module, what else? Yeah, I created the shader module. Let's go. Use if in declared identifier. Now this becomes shader module. Okay. Pnex, I don't need it now. Code, undefined, map. Okay. This should be called just shader. I'll say just info. Okay, it's very clear from that. And now this could be just called handle. Alright, and then finally return return that struct. And basically handle is equal handle, allocation callbacks as always. I also would probably make a snippet for this one too. But anyways, let's see what else. I think, oh yeah, device is equal to self. Probably, and there you go. Now in shader module, I'm just going to make sure I have I guess handle, allocation callbacks, something like this, and finally something like like this. Oh well, I jumped very away just to do that crazy stuff. Okay, my bad. Right, well, there you go. Now in the init function, I could just say self.device.dispatch dot device. No, destroy module, destroy shader module. And yeah, now what's next? Defined. Alright. We probably need the handle of the device. and then we probably need the self.handle, and then we probably also need the allocation callbacks finally. And yeah, that's probably it. Let's go. And now instead of this craziness right here, what we could just say, let's see, we could just say const vertex shader is equal to shader, oh well, device.create, oops, what? Where's the create shader module function? Did I place it in the, oh yeah, I placed it in the wrong section. Let's put it inside the device. Const, let's go. Okay, there you go. And what the is going on here? I think maybe I pasted that or what? What? Oh yeah, never mind. Just so you understand my point, using self everywhere can make it harder to read the code if you have to look up what self means. I mean, I think self is kind of like, what can I say? Something like agreed upon, like I think most Zig coders actually use self. And even if you're coming from Rust, that's pretty much the thing there. And in fact, in most languages, it's pretty clear when you see self what it means as a type. So yeah. Create shader module. I think we could probably just say this. Asset shader vert. Allocation callbacks, null. As always. And I think that's pretty much it now, just for the second one. And instead of, just gonna paste this instead. And then call this fragment shader. Well, a vertex shader module just for completeness. And there you go. And use local constant. Well, of course, defer vertex shader module dot dinit, and same thing with the other guy. Oopsie, let's go. All right, and that's pretty much it for shader modules. Now let's go to the next one. Honestly, I don't know why I didn't think about just going through every page, trying to explain a bit about that, and then afterwards get coding, which also helps me kind of review the things that is there, and also you understand what the heck I'm doing. So anyways, all right, amazing. And now after that, they're doing shader stages. Now, okay, let's actually do shader stages. Why not? So for shader stages is basically like this is equal to c.vk shader stage. What do you think? Should I just keep on coding, or should I go ahead on every page on the tutorial, try to explain to you, like trying to give you more details and a better or more intuitive explanation, or at least my own kind of explanation about the page? Of course, I'm not reading through the tutorial, I'm just explaining the stuff that inside of it on my own way. Or just keep on coding. Let me know. Let me know. Of course, it's gonna take us more time to actually keep on explaining every page in the tutorial. But I think it helps me myself to review the actual details, and second, it helps you as the viewer to actually understand what's going on. Okay, so vk shader stage create info, I think. All right, so what's going on here? Oh, module flags, pname, pnext, specialization info stage. All right, so honestly, why not return pipeline shader stage? Ooh, interesting. All right, gotcha. Makes sense. I think what I'm going to do, maybe for this one, is to basically go back to that struct. I think I'm going to create like a git shader stage or something like that. Or honestly, maybe just call it shader stage, but anyway, whatever. And here I'm just gonna call it VK shader stage, I think. Right. What's going on here? I guess pipeline shader stage. Something is wrong here. C.vk pipeline shader stage. Okay, there you go. I think you're wrong about self being idiomatic zig. It is, yeah, idiomatic. That's the word that I was missing. It's common in Rust and has spilled into some zig code bases. If you search the lag graph for const self equal this, you find exactly one occurrence. Okay, interesting. So yeah, sure, why not? I guess we'll do it. But what about just using this instead of self? What do you think? Pipeline shader stage creates flag bits. Oh, what the? No, create info. Right. I like the in-depth take. Your videos are already very tutorialish, and that's a good thing. There's not so much material on Zig programming. Yeah. So at first I was kind of started just, sharing with you me basically trying to code the project. It's not a very easy project. And in fact, from now on, that would be the content of my channel mostly, which is to basically just trying to do something like, for example, create a programming language, or trying to mode a game, or trying to create a game, or trying to create a server, or something like that, and just showing you what it takes, basically. I'm not suggesting that you should change your code, just a heads up. Yeah, it's always nice to tell me, like, if you guys have any suggestions, let me know. Especially about the structure of the code. But yeah. All right. So anyways, the module is basically self.handle. And of course, well, self void. Well, actually, vk pipeline shader stage. There you go. And here we gotta actually return dot that guy. And yeah, right. What else? Yeah, ZLS is not helping when you do that. All right, let's see. Now we have pnext equal null, and also we have pname. Now this is the actual entry point name. Entry point name, which is usually idiomatically called main, but you could change that. And then there is pnext, there is module flags. I don't think there's any special flags there. Specialization info is quite interesting. Basically, you could, what specialization info? I mean, it's kind of a little complicated, but I'm gonna try to make it in simple layman terms. It's kind of basically like C preprocessors or like Zig comp time. So instead of creating two shaders, just with, like, I would say it's idiomatic to rebind itself in a function which returns a type. It's idiomatic to rebind itself in a function which returns a type. All right. So as I said, specialization info. So instead of creating, for example, a lot of variations of the same shader. Now the thing is, in the shader, if you use an if condition, then you're actually harming performance, because every single condition counts. And especially in GPUs, they don't like branches so much, especially the older ones, because whenever you have branches, you kind of get in the way of parallelism. You kind of almost want to use mathematical expressions instead of, kind of like imperative. Yeah, it's fine, Travis. Thanks for the heads up. Okay. Specialization info. So instead of saying if conditions, you know, on some variables in your shader which would harm the performance, you could kind of use specialization info to have, you'll still have the same source code, but instead of having a runtime branches, you kind of somehow do compile time branches, kind of. And basically you could use this specialization info field here to kind of like instantiate, kind of like C++ template, instantiate the shader in another specialization kind of thing. So yeah, hopefully that just gave a little I hope that that you understand something from that. But anyways, oh yeah, I forgot a stack though. Let's see, c.vk structure type. Let's see, and then we have pipeline shader stage create. Let's go. And what else? Is there anything else that is interesting there? There is stage. Alright, let's see. For the stage, it's basically, is it a vertex shader? What exactly it is? So where is vertex, etc., etc.? What? Let's see. Don't remember what it's called. Actually, I think I have it here. Okay. Where is it? Where is it? Where is it? Where is it? Oh, not here. It's probably here. No. Let's just go ahead and search for it anyways. Create info. Oh yeah, Rust. There you go. And stage, there you go. And let's go. This is all the stages that are in the core of Vulkan. And the fuel is done. The programmer fuel. Okay. Oh, what? Stage all? What the? Oh, I think maybe you could do that when like you have the same shader module but with multiple entry points. Ooh, interesting. There's also all graphics, but anyways, we're just gonna go with the normal way. All right, cool. So we pretty much need vk shader stage flag bits. Vk shader stage. Okay. All right. So I have here entry point name, which is should be what it should be. I'm just gonna go with this guy. And that's the entry point name, which is probably gonna be main. And then finally the stage. And honestly, I'd like to have the stage first. I'd really like for Zig maybe to add default parameters. That would be nice. But anyways, so here we just gotta go with cint, I think, pretty much. And then here we're just gonna go with the stage. Right. Okay. So now we could go back to our shader. Let's go, and now we could just say const shader stages is equal to, well, it's an array of c.vk pipeline shader stage, I guess, create info. Let's go. And now I could too simply say vertex shader module dot what? Let's see, vertex shader module dot get. What? Why? Oh, I need to try this out. Let's go. There you go. Get shader stage, and then here we could say vk pipeline shader stage vertex, I believe. I don't know why it doesn't. What the? Shader stage vertex. Okay. Oh, there's no pipeline there, just shader stage. Okay, cool. So in this case, vertex is that. Cool. And now the entry point name. Let's see, entry point name is usually the, what is the name? What is the word again? Let's see, idiomatic. Yeah, it's the most idiomatic, pretty much, to call it main. Anyways, now pretty much gotta do this, a similar thing with shader fragment shaders module. To get shader stage, c.vk shader stage fragment bit, and then finally the entry point, which is usually again main. All right, now we just gotta put these in an array for later on, and we're good to go. What is going on? All right, cool. All right, so that's pretty much it, I think. Now I could make this a little nicer by doing this and doing this. Basically, if you add a trailing comma, you get a much nicer formatting there. So yeah. All right, any questions so far? So we have created the shader stages. This is one of the stages to creating a pipeline. Preparing your modules. Okay. What's next? Watch next. Let's go back and now to the next explaining. All right, fixed functions. Now we have prepared the programmable stages, which are basically shaders. Now we're gonna go with the fixed functions. Now, by the way, like for example, the programmable stages that we have in our today's GPUs, in our modern GPUs, back in the day, they were fixed function too. Like vertex, fragments, they were all fixed function at some point. So what means fixed function is that instead of actually writing code to handle the vertex shader yourself, and like the vertex stuff yourself and then the fragment stuff yourself, you just had some knobs to tweak, you know, and some options basically, but everything else is up to the hardware, either like hardwired in the hardware or the driver is doing it for you. But nowadays most stuff is programmable, but now we gotta explore the fixed functions. All right. That's why if you looked into like very old, you know, like compatibility OpenGL, you're gonna find things much easier because they were fixed stuff, like they were fixed functions. But the problem with those is that you don't have a lot of flexibility, you know. It's like instead of having a programming language that you could actually express code in, you just have a GUI like a plugin or something. So yeah, pretty much. Let me try to show you something just for the sake of it. OpenGL compatibility, just to show you how much the difference between the old stuff and today's stuff. Let's have a look into OpenGL compatibility triangle. Let's see. I wonder if I can even find it at this point. Let's see. Why it's showing me core when I said compatibility? What? Are you kidding me? What about this? Let's see if this is compatibility. I don't think. Well, that's not what I was thinking about though. I don't know. I couldn't find the example that I was looking for some reason. But anyways, whatever. All right, let's go to the next step now. So we have dynamic state. All right, now there's fixed state and there's dynamic state. Now, what is fixed and what is dynamic? You choose depending on your application and the trade-offs you want to make. Now, stuff that is fixed or static instead of dynamic, if you want to change those, you have to actually recreate the pipeline from scratch, basically. The stuff that you make dynamic, you do not have to recreate the pipeline to change them. But the catch is you may impact the performance. For example, here they're making the state viewport and the state scissor dynamic instead of static or fixed, which means that we can actually change the viewport size and the scissor size and the other properties without having to recreate the swap chain. Now let me give a little example. For example, let's say you're going to have a game that the whole mechanic is about resizing the window. Then you surely don't want to recreate the pipeline every time the player resizes the window. You probably want to go with dynamic state. But let's say on the other side, you have a game that is usually like a game basically, and probably even full screen. Like usually the player wouldn't actually resize the window, and even when he does, like just for some time and that's it. At that point, you don't really want to take the potential performance impact of making the viewport and the scissor, for example, dynamic, basically, instead of just recreating the swap chain, because it's just something that happens in, it's not like, I don't know, it doesn't have to be fast for your own game or application, basically. So it's just basically a trade-off between having to recreate the pipeline, which is a really slow process, and performance, basically. Hopefully that makes sense. In this case, we're just making the viewport and the scissor dynamic. So we could basically choose those and change those at every frame without having to recreate the whole swap chain from scratch. Okay, now we have the vertex input, the first stage that we talked about earlier. And currently we're not gonna do anything about it right now. Nothing fancy there yet. Later on we're going to use that, I think. Yes, and now here, the input assembly. And by the way, why we don't need to care about this right now, because we don't have a buffer of data. We already embedded the data in the shaders themselves for now. But later on, when we're going to have a shade, like a buffer, we have to actually describe the format of those vertex attributes, etc. So we probably want to use this guy. But right now we don't, since we don't have any data coming in. It's all embedded in the shader, in the assembly. So in the SPIR-V. Anyway, input assembly now. Now in the input assembly is how you want to assemble those inputs. Like at this point, you have got all the vertices, the vertex or the vertices. Now, how do you want to assemble them? Like, for example, you could choose between these topologies. There is point list, line strip, triangle list, triangle strip. Now, usually, and most of the time, you want to use triangle list. I think, in fact, you probably just want to go with triangle list. Like, the other ones just doesn't worth it most of the time, honestly. So basically, triangle list, like you would have every 3 vertices will be their own triangle. But for example, let's say a line list, it would make a line between every vertex. And then there is like point list, which would basically just a dot on every vertex. And there's also triangle strip, which I believe, if I remember, oh yeah, So like instead of having to go, hold on a second. Triangle topologies. I think they could have probably included a much better, you know, thing here, but let me show you. And hold on, let me actually see here if I can find something good. Oh, it shows me the network topologies. No. Graphics triangle, or graphics topologies, I guess. Or we could say OpenGL topologies or something like that. Let's see. OpenGL topology. I only found one, seems like. Okay. Oops. Oopsies. Where is the guy? There you go. Okay. There you go. So this is point list. Here's your vertices. Now in point list, as you can see, this is what happens. In line list, this is what happens. Each two vertices becomes a line. Line list adjacency, I'm not sure what's that. Anyways, and line strip, you basically, instead of having to define two vertices for each and every line, now you just define 0, 1, 2, 3, and then it would actually link all of those in one line. Line strip adjacent, I don't know what's that. Triangle list, there you go, there is the winding order. Alright, triangle list, triangle strip. And triangle strip is basically define these like this: 0, 1, 2, 3, 4, 5, 6, kind of like zigzag. And then you just create those triangles pretty much. Hopefully that makes sense. Alright, so that's pretty much it, I believe. Does that make any sense to you? Let me know. Topology. Input assembly. Primitive restart enable. This is this won't be useful if you're using, for example, triangle list or point list or line list. This primitive restart enable can be useful when you're using triangle strip or, let's say, line strip, basically. And you know why? Because when you're using, for example, triangle strip, the triangles will always be linked. You cannot unlink them. Like, you just cannot make individual triangles by themselves. You have to, like, the way it is done, they have to be linked together. But you can in fact change that by adding a special value in your index buffer, and that would basically tell the thing to actually split up your geometry at that point, so you could actually start a new triangle strip basically. And for that to work, you'd have to, of course, as I said, use a special value in your index buffer, but also where is it? Where I was? Oh yeah. But also make sure to enable this primitive restart enable. But most of the time you just want to go with triangle list, and this is not enabled. So viewports and scissors. 0 width, height, minimum, max depth. Okay. So viewport. This is viewport. And this is scissor. So basically scissor kind of like just frames what you want to draw. Like basically when you actually, for example, let's say resize the viewport, you can see that the image got scaled here, you know, because actually you're changing the coordinates there when you change the viewport, as you can see here. But then here, when you change actually the scissor, you just kind of like just cut where you're rendering. You kind of pick the area where you actually want to draw, and the other area. You just want to discard those fragments or whatever, basically. Of course, you can set the areas using offsets and extents, basically. So rectangles, rects. Viewport state, viewport count, scissor count. I believe if you want to use multiple viewports, you'll have to actually enable a feature. Right, viewport count, okay, scissor count, rasterizer. That's the rasterizer, okay. That's the thing that actually tells you which, I think which pixels you actually want to draw into, or maybe they're called pixels technically, I don't know. But anyways, so this is not very interesting for our cases, although this may be useful for more advanced cases. The only thing that is quite interesting is polygon mode. Polygon mode here, you can set it to fill, line, or point. If you say fill, well, you just get the normal stuff you expect. If you say line, you'll actually start rendering in wireframe, you know, instead of filled triangles. You'll see wireframe. So let's say, for example, in your engine or your game, you want to switch between wireframe and what else? And normal mode, you know, filled mode. Then you could basically either create, like, let's say 2 pipelines with different polygon modes here, or you could look up on how to actually make a dynamic state, although maybe you may need a feature or something or an extension to actually do that, I'm not sure. For line width, oh yeah, there you go. Using any mode other than fill requires enable a GPU feature. Oh yeah, in fact, to even use other modes, you actually need to enable a GPU feature. Line width, basically when you actually choose the line, kind of like when you choose to draw lines instead of triangles, you can actually here in the rasterizer, you can set the line width, but you can only set it, I believe, to 1 line. Yeah, I think between 0 and 1 maybe, not sure. But either way, but if you want to make it thicker, then you have to actually also enable a GPU feature called wide lines. Let's go. Now here, the call mode. This is what I was talking about before. The call mode here, which face you want to call. Do you want to call the back face or the front face? And also you define which is the front face. Is it the clockwise order of vertices or the anti-clockwise? This is what I was talking about before. So usually in games, you would probably set it to vacay call mode back. And honestly, you would usually use anti-clockwise. I'm not sure in the tutorial why they're using clockwise. Even in mathematics, I think they're using anti-clockwise. But anyways. But it's up to you pretty much, but I think you gotta change some math, etc. Like how you do math, basically. But anyways, or you could just say vacay call none, I think, which basically won't hide any face. Both faces will be shown, and if you are calling like a face, and you cannot see any geometry, although you expect to see something, then maybe it's worthwhile to actually make the vacay call mode none to see if you have a problem with the actual order of vertices or something like that. So as a beginner, you probably maybe want to start with vacay call mode none, I think. But anyways, depth bias, that is not very interesting for us right now. Multi-sampling. Here you can, yeah, I think I will probably do that later on. But this you can use this to actually do MSAA, you know, like multi-sampling. Like, you know, when you see a triangle and it's very rigid, you know, like you can see the individual pixels, it just looks so sharp. Let me actually show you. Hold on. Let me try to find an image. Multi-sampling. Let's see, there you go. I'd like to find a better image, hopefully. Oh, or maybe I do remember in the tutorial itself, I think there was some good illustrations in, just as a quick thing, multi-sampling. Yeah, there you go. So as you can see, if you actually zoom in very closely, you can find that this is what you get without multi-sampling. It just looks so sharp on the eyes. But if you use multi-sampling, which basically instead of sampling in one spot in the center in this case, you sample from 4 spots, and you do that by basically rendering into a bigger image, kind of, I think, if I remember well, or something like that. And then you basically, instead of sampling one place, you actually sample 4 places per pixel, or per fragment, should I say. And with that, like if 2 samples are on and the other are off, then you get like 50% opacity. If one, you get 25% opacity, and with that you get this smooth feel to it, very, very smooth. But yeah, and this is how you actually do it, but we may do it later on. Anyways, that's just a little look up into it. Anyways, depth and stencil not needed right now. Color blending. Oh yeah, this is where you actually blend the what is it called, the fragments, I think. Yeah, so as you can see, since this is not a programmable stage, this is a fixed stage, so instead of actually writing a formula of how you want to blend those stages, which would be nicer here, no, you actually, or in fact you could probably, well, no, but basically instead of actually programming some formula, you have to basically configure some knobs and some options here to actually make it work. It's kind of like here you're writing a formula using flags and options basically. It's not very useful for us right now, but if you want to handle transparency, which we'll probably maybe do later on, we can go back to this and revisit this. But this is kind of like, basically, it kind of translates to this code right here. If you just see this code right here, you probably understand what's going on. But anyways, right now we don't care about opacity, like transparency. Okay, never mind. So RGB, enable, logic, pipeline. Pipeline layout. Pipeline layout is not very interesting for us right now because we're not using buffers. And in fact, if we were using buffers, we also have to care about descriptor sets and descriptor layouts, etc. Something like that, which is just a lot of work that I'm glad we don't have to do right now. Okay, so I think let's start with let's go from start. Okay, now let's actually program this. First of all, we gotta deal with dynamic states. All right, cool. Let's get the dynamic states up and running. Const dynamic states is equal to c.vk dynamic state. There you go. C.vk dynamic state. We'll go with same as the tutorial, why not? Dynamic state scissor. I think that's it, right? Yes. And those are the dynamic states, pretty simple. Oh, well, we still have to actually go and fill that guy. Okay. So const actually dynamic state. Oopsies. Dynamic state info is equal to c.vk dynamic state info, I believe. There you go, great info. And then here we need the, first of all, s type as always, dynamic, there you go. And then p next as always, null, and then finally, well, not finally, but count dynamic states dot len, and then p dynamic states is equal to address of dynamic states, and then flags. I don't think that's very interesting right now, so we're gonna go with 0, and there you go. Pretty much that's the dynamic states. Pretty simple. Vertex input, it's pretty much just optionals right there, as you can see. So yeah, const vk pipeline vertex input, vertex input state, well, vertex input info, let's go with that. Vertex input info, there you go. Is there any questions so far? Oopsies. Input. Bruh. What? There you go, finally. I should have probably just wrote it myself anyways, instead of trying to guess. Okay. The other stuff would probably pretty much be 0. In fact, even p next is null. So we could pretty much use here cd.mim.0 init until we go back to it when we need it. There you go, and there you go. And there you go, pretty much. Now the input assembly. It's pretty much vk pipeline input assembly. One other thing about using another language than the tutorial is that you cannot copy code. You're forced to actually write in everything. Hello, well, welcome to the live stream. How is it going? Where are you from? I'm from Morocco. Okay, pipeline input assembly. Const input assembly is equal to c.vk input assembly states. Are you a programmer? What do you think? Assembly states great for s type is equal to vk structure type pipeline vertex assembly. There you go. P next equal null, and then what else? Flags 0. Primitive restart enable. Topology, that's what's interesting. Bro, why so colorless config? What do you mean? Vk topology triangle list. Oops, not triangle fan. Triangle list. There's even triangle fans. I mean, the VS Code color scheme, everything is white. What? Everything? You mean everything is black? I guess. Well, c.vk primitive topology. I think that's all what I currently actually need from this guy. So in fact, let me leave that there, and then let's just say this cd.mim 0 init dot, and then finally bring in this type and then put it here. And yeah, I should honestly do some what is it called, snippet for this probably. Do you like Zig instead of something like Rust? I like both Zig and Rust, although probably Zig more, especially for my own projects currently. But it depends. For example, if I were to write, let's say, a server, a production server, I would probably pick Rust, at least for now. But it really depends on the project. I'll probably make a video about that later on. So yeah, input assembly. Now we got the input assembly up and running. Now the viewport. Cause viewport is equal to c.vacate pipeline. Well, viewport, let's go. Here we got the x and the y, 0. And then the thank you, bud, much appreciated, such a friendly streamer. I wish you all the best. Thank you so much. Thank you. Width is equal now. Now the width, I think, yeah, we need to get it from the swap chain extent, but the thing is we didn't store that. So let's actually have a look into the extent. There you go. So image extent right here. So here you could basically store the image extent like this. But of course we gotta add that. Image extent. Image extent. What it was? Extent, I guess. 2D? Right. I think so. So right now I stored the actual image extent of the swap chain, but oh well, interesting. Are you making a game engine or just a renderer? Pretty much a game engine, and probably in the hardest way possible. Oh my god. Oh well, in fact it's not a game engine, but pretty much I'm just trying to figure out the graphics right now. I'm still with the graphics. I'm using Vulkan, so it's pretty rough. Like around 700 lines of code right now, and still we didn't get to triangle yet, so I guess that makes sense. So alright, now the thing is, I don't really need, how much math do you need realistically to build a game engine? Well, depending on how complex you want that that game engine. It's like graphics, like really, as I said, depends on how much complex you want that engine and the type of game engine. If you, for example, you want to make a game engine for, let's say, a scientific simulation, then bruh, you really need a lot of mathematics there. Unless, well, not necessarily how, let's say, you calculate math or do formulas. You could probably find libraries out there to help you with that, but at the very least, know your tools. Like, know what you could use, let's say, a sine wave for, or a cosine wave for, or let's say what you could use matrices for, like what happens when you multiply a matrix with a matrix, let's say. Not necessarily how to actually calculate it by hand, because that's probably done for you in a library, unless of course if you want to write a library on your own, like a mathematical library on your own. But as I said, it depends really on the complexity of the project. But honestly, personally, I learned a lot of math just from graphics programming, especially from shaders. You know, like if you go to shader toy, yes, shader. So there is 2 websites that I recommend for mathematics though. Is first of all though the Desmos, right? This graphical calculator is very interesting, you know. Just play with it, you know, just like, for example, you create a sine wave on, let's say, bx, you know, do some form, for example, and then you can create some variables, and then you play with those variables and just find out what happens. Like what happens when you actually make a bigger, or what happens when you change b, or what happens when you change c, and what happens, let's say, when you change d. You know, just play with functions and try to figure out what everything does. What when you change something, what happens? And there you get some intuition for functions, and that is very great. And you could even simulate some variable, let's say, for example, and then you can find out what happens when that variable becomes something, etc. and you just, you know, experiment with such tools. There's even a 3D graphical thing like that. And the other one, this is hardcore. Okay, shader toy. Not necessarily shader toy, but shaders in general have taught me a lot though. I'm not sure if I'm allowed to actually show this though. But basically there's people out there that use math with shaders to actually create some crazy stuff. Like all that you see here is just math with shaders. All you see here is generated mathematically. Like mathematically using a fragment shader. It's like it was very hard to actually start understanding how to create useful fragment shaders and interesting fragment shaders. But once you really learned a lot of mathematics along the way of learning shaders, although it's very rough at the start though. But there you go. So the problem that we have here though is that we don't necessarily have a swap chain yet. But the nice thing is that we do not have to probably provide a viewport though. We really do not have to. And you're welcome. Well, thank you so much for the question. Okay. So as I said, since we already made the viewport a dynamic state and the scissor a dynamic state, we don't really have to specify the viewport while creating the pipeline, because we're going to be doing that every frame anyway, as you'll see when we do that. So there's no need in fact for specifying the viewport and the scissor right now, because it's dynamic state. So that's nice. It's already problem solved by itself. Okay, cool. Viewport state, but they're doing it here anyway for some reason. Well, whatever. And here we got the rasterizer. Let's go. Const rasterizer. As you can see, you get to actually tweak and configure every single detail of the whole pipeline of what happens in the GPU. That's why you get a very big code, and it's very time consuming, but you really get to tweak every single knob. And in fact, there is even some extensions that you can enable and some other features that you can enable to get even more control. For example, the swap chain. As I said before, there is an extension to actually handle the swap chain yourself instead of leaving the OS or the operating system. Okay, I think the live stream have reconnected. Let me know if the live stream is fine, because it seems like I got notified that it disconnected for a second there, but then hopefully it's reconnected now. Let me know. Someone tell me if the live stream is fine. It seems to me that it is fine now, but let me know. All right, anyways, so let's actually create the rasterizer stage, or what it is. Oh, hold on, what is it called? Let's see, it's called pipeline rasterization. Okay, rasterization create info, I think. Okay, great. Well, there is a lot of stuff here, but we're just going to do what we need. So of course, as always, stream is fine again. Yeah, thanks. Okay, great. Pipeline rasterization. There you go. Nice. Next up is pnext. No, well, I don't need it. Probably going to use a 0 init once again. And is also, well, what else? What else we require? There's a line width. I don't know if that really required. Probably. Anyway, so what is very useful for us here is the front face. So vk face or call Yeah, call mode. Okay, you can actually use all of these. Back bit, front and back, if you want to call the front and the back face. So both. I don't know why you would want to do that. I mean, you pretty much want to have anything, any face at all. You want to have anything like drawn with this. I don't know why would you need that for, but yeah. None basically would not call anything, which means that the two faces will be visible. So let's say you rotate the triangle, the two faces will be visible. In my case though, I'm just gonna go with, I think, front bit. Back bit. But later on, if for whatever reason we didn't have any triangle show up, we'll try to basically disable calling and see if we have a problem with the actual order of the vertices or something like that. That's just something to watch for. But if you want to stay on the safe side, you can say vk call none. But anyways, polygon mode. This is also quite interesting, although not. We need a feature enable, I think, if we want to use this though. But for now, it's gonna go with fill, which you don't really need to enable anything. Other than that, the other things, I don't think they're quite interesting. Yeah, the other things aren't very interesting for us currently. So yeah, I'm just gonna use this guy again. Ooh, it's much easier this way, I think. Yeah, much easier. Don't know why. Well, anyways, so that's the rasterization. Well, that's actually should be called rasterization state or info. Let's go with that. All right, what's next? Multi-sampling. Multi-sampling, I would probably do multi-sampling after we got a triangle, maybe. But now we don't really care. So probably vk sample count 1 bit is default, maybe. We'll see. Anyways, so let's actually get the multi-sampling info. There you go. So let's see, cd.mim. Well, honestly, let's just start with this guy. vk multi-sampling. Oops. What it is? Multi-sample, it's called. Is it? Yes. There you go. Well, great info. Okay, great. Now the S type is equal to vk structure type, and then multi-sample. There you go. And then what else? What is other than that? There is rasterization samples. Make sure that's sample 1 bit. Yeah, it's not default. So it's 1. So we cannot actually discard it. Okay. All right. What else? Minimum sample shading. Sampler mask. I don't think the other stuff is useful for us right now. Yep. Pretty much just the S-type and the other guy. And just like I did before, I could basically say this, and this. And there you go. Done. Next up, the color blending. All right, color blending. Let's configure that stage 2. Color blend. Attachment. Oh yeah, color blend attachment. Interesting. Okay, color blend attachment info. or just color blend attachment. And let's use c.vk color blend attachment. And pretty much most of these would be discarded for now because we don't need them. They're just optional. We just need to basically make sure to have this color right mask. Color right, oopsies, mask. And swizzle, yeah, vk color component. There you go, okay. So basically just gonna make sure to set all of them and order them together. R, G, B, and A. Though I'm not sure about A. Yeah. Okay. We're going to go back at some point for this when we care about transparency, but for now. Just make it work. So basically what this is called an attachment, color blend attachment, and you'll actually have multiple color blend attachments and then have a bigger color blending kind of thing. Why? Too simply because you may have multiple frame buffers that you would like to attach to your fragment shader, and you'll have basically a color blend attachment, a different color blend attachment for each one of them. In our case, we only have one attachment, which is the swap chain image. So yeah. Yeah. Color right mask. I think that's pretty much it. Yeah, vacate false, all of them are optional pretty much. And yeah, gonna come back to this later on. Okay, this is if you want transparency, I think. Yeah, yep. I'll try to, basically here he's doing interpolation, so anyways. Now the actual color blended state. Do I need a S-type? No. Interesting. Color blending state, okay. Color blending state is equal to c.vk color blending. Oops. Color blend state create info. So it should be called color blend state though. And this one does need an S-type. Alright, color blend state info. And then you need the pretty much only the attachment count and the P attachments. So attachment count is equal to, well, currently just hard code 1, and P attachments is well, there you go. All right, so that's pretty much it. We may want to actually create an array instead and make it more generalized, but who cares anyway now. Okay, so other than that, and finally, we got the pipeline layout. This is the latest one before actually creating the actual pipeline. So yeah. All right. And oh, I need to actually probably use, yeah, I need 0 init here and here. Okay. Okay. And here. Only here. Okay. Great. Next up is, as we said, well, pipeline layout, which is gonna be empty for now. But the thing is, we need to actually load the function pointers that we need to create a pipeline state. So let's go ahead here, copy a couple of functions there, And there you go. And now let's actually make this create pipeline layout, I guess. Let's make sure that's the case. Oops. Honestly, Vulkan needs a Vim user. Destroy pipeline layout. To type all of this out. Alright, vk destroy pipeline layout. Ooh. A Vim Jika charge. Create pipeline layouts, destroy pipeline layouts. Alright, nice. So that's pretty much it for that one. And next up though, anticipating for the future, we're also going to have the pfn vk create pipeline, graphics pipelines. Create graphics pipelines, and then finally, in fact I could just copy this guy instead. In fact, destroy pipeline. Oops, and there you go. There you go. We have loaded the function pointers. Now let's go back to where we're using Project Lemon Juice. If it takes this much code for a render, imagine try to render entire video. Vulkan got you doing way too much. I mean, rendering a video, like decoding, encoding, and stuff like that, and rendering videos is complicated just by itself, even using very great libraries. So I don't know how it would be in Vulkan. The nice thing about Vulkan is that you don't really have to care probably about the nitty-gritty details of encoding and decoding. This probably would be done for you if you're using, of course, if you're not doing it yourself, if you're using the actual Vulkan video API, basically using the GPU to do this stuff for you, I think. But I never really tried it, so I cannot really say much about that. Okay. Well, create graphics pipeline. Let's see where we were. Well, attachment, let's go. Now let's actually create a pipeline state. Oh, Vertex state, I think, or what is it called? Yeah, pipeline layout. Okay. Pipeline layout. Well, in fact, should be variable. There you go. It's gonna be a vacate pipeline layout. And there you go. That's the pipeline layout. Now we gotta actually create it. Map vk error device.dispatch create graphics create pipeline layout first, and then here what we're gonna say. And oh, by the way, try this up. Okay. So we probably need here the device handle, as always, and then probably the allocation callbacks, and then finally maybe pipeline layout. Oh, I forgot about the info though. Yeah. So info. Well, let's just call it layout info, I think. Okay, const pipeline layout create, oh well, info. Let's go, s type as always, c.vk structure, pipeline layout create, and then yeah, I think I only need that guy pretty much. So I think that's it for that one. Now, of course, you'd like to defer. Let's see. Device.dispatch.destroy pipeline. And oh, talking about destroying, I think I forgot one little thing before, but I think it doesn't matter. Yeah, it doesn't matter probably. Okay, never mind. Destroy pipeline. Now what's next? Let's see. First of all, the device as always. Device handle. And then the allocation callbacks. No, the pipeline layout itself. I think. And then the allocation callbacks, which is null in this case. And there you go. Now hopefully we got a pipeline layout. Next would be creating the actual graphics pipeline. Require address of the cores to slice type. Address of, okay. Would that help? I should have tested that one though. Oh well. Expected type found const. Alright, let me actually do it. What it's doing. Okay, let me just say this. I don't know why I didn't test it before. Vertex shader code. Const vertex shader code. I think it was like this before. And in fact, maybe even this. Right. And then finally, let's grab this guy. Oops. Well, did you guys sleep yet or not? Fragment, shader code, shader frag, SPIR-V. Yes, and then what? Alright, and here we gotta say fragment shader code. Yeah, pretty much. Now, let's see what's gonna happen here. Come on, expected type U8 found const. Oh, I do remember that if you want to take a slice, you maybe do something like this, if I remember. I believe there was also another way, but expected type found const, or maybe like this instead. What? Okay, I'm just gonna do it the normal way, honestly. Just grab this guy. It's gonna be a const array. Const array. Well. Okay, I think like this. Alright, let's see. Expected type const found const U8. But hold on. No. It's not how it works. I mean, it should do this now. No. Maybe you gotta pass those like that or what? This is stupid. Array literal requires address of operator to coerce a slice type. Interesting. Expected type U8 found. Const. Weird. 0. Expected type U8 found. Const. Cast discard const qualifier. What? Oh, I think maybe I know what's the problem. Let's see. Maybe I need a const here. Okay. Const U8 has alignment 1. Const U32 has alignment 4. Use align cast. Okay. I guess align cast. Well, this is asking for trouble. Oh. Expected type swap chain found. Shader module. Oh yeah. VK shader module. Okay, what else? Expected type CU int found C int. All right. What else? Misinstruct field flags. All right. 0. What else? Misinstruct field specialization info. Bruh. Equal null. Next. What? Oh yeah, I need to use a 0 init here, forgot. There you go. There you go. Nice. And layout info. I think it's probably gotta be an address here. And what else? Oh, destroy pipeline I used. No, pipeline layout. There you go. And yeah, it seems to be work. What the? You have seen the glitch? Linux is weird. Linux is weird. Oh, well. Yeah, there's no validation layer problems, right? Let me make sure that's the case. I don't need this anymore. Let's get vk config. Oh, that wasn't running? Interesting. Let me go ahead and do this and then make sure validation is on. So if there's any stupid problem we have done, we can catch it in time. And yeah, seems like everything is great. Amazing. All right, amazing. So now it's the time to actually create the pipeline, finally. Const, and you're gonna also notice here that in Vulkan, it's pushing you towards creating a batch, like groups of pipelines at a time instead of one pipeline at a time. So let's go pipeline equal to device dot. Well, in fact, what I'm doing, var, let's see, var pipeline, it's c.vk pipeline is equal to undefined. And now we're gonna say try map vk error, and then what I'm going to do here, device.dispatch, oops, dot create graphics pipelines. Let's go. And then what else here? Let's see. So we need all of this stuff. Okay. All right. Now let's put these guys there. Well, first of all, we need the device. Well, sorry, device.handle, and oopsie, then the cache. In our case, I think it's gonna be null. And then here, how much pipelines you're gonna want to create. And here, the pipeline create info, where we basically just assemble all of that stuff together. For here, it's const allocation callbacks, I believe, for every pipeline maybe. And then here it would give you all the pipelines in an array, of course. But in my case, I'm just going to go with one pipeline, so I don't need to allocate anything really. And now we have a pipeline. Now we're basically going to create the vk graphics thing, the create info, which is just an assembly of all the stuff that we have prepared so far. So, okay, well, if no, const if no equal to, well, c dot vk graphics. Let's go. Oh well, these are useless. I mean, let me actually show you the tutorial though. Next, and oh, he's creating the render pass first. Oh yeah, I forgot. I gotta recreate the render pass first before creating the pipeline. But let's just go ahead and try to do it, I guess. Okay, well, let's actually create the render pass first. I quite forgot about that. We also need that to actually create the pipeline. So I'm just gonna comment that out for a second there. Now let's try to figure out the render pass. Now the render pass, at least in my view, is kind of like just taking the swap chain images and then the, what is it called, the pipeline, I guess. No, hold on, let me see. Lloyd OP attachments, forgot what I wanted to say. Yeah. Subpasses attachments. So the render pass basically, I think, links maybe the pipeline and the shader. Well, I don't know what I wanted to say before, but anyways. Okay, let's try to create that guy. Let's see. We have, first of all, we're going to create a color attachment. And the format, of course, is the swap chain image format. Because basically we're going to, yeah, it's for the render, like for the swap chain, right? And then sample count 1 bit. We are not using multi-sampling. Lloyd OP clear. The first operation would be to clear it, to clear the image, to clear the actual swap chain image. And the store OP is to actually keep the rendered data that we rendered from the shaders. And then stencil, we don't care. Now here the initial layout. First, all images are in defined layouts, I think. And then here we are going to basically transfer it to the present src-khr layout, which is required to be able to, you know, send your image across to presentation, basically to present it on the swap chain. Okay. What else? Subpass and attachment references. Subpass is interesting. Remember when we had in the shaders location equals 0, location equal 1 for out color? You know, here where it is. Let's see, shader dot frag. Okay, remember this guy right here, out color? Here we said location equal to 0. Well, here that gotta be the same index basically. So attachment is equal to 0. Layout, here layout color attachment optimal, because basically we're going to render to that image or to that attachment, so we have to do this. Right, cool. Cool. And then what else? There is subpass, pipeline bind point. So here you either say, well, you bind it to graphics or compute. In our case, of course, is graphics. Color attachment, how much color attachments you have? In our case, we only have one. Yeah, I kind of remembered what I wanted to say. Render pass is basically like a kind of like a template or a blueprint for your shaders in some sense, I guess, if that helps even. But at least that's how I like to think about it though. But so the index of the attachment is array. There you go. Okay. All right, nice. So if you want to look, for example, later on we want to actually use to use textures, we probably want to use input attachments here maybe. And then resolve attachment. We will use this for multi-sampling. There you go. And that depth, of course, depth anyways. Preserve attachments. Oh yeah, this would be used for, yeah, I think we'd probably use it for multi-sampling, because you probably like have a kind of like an intermediary image that we don't really need to store the content of later on. So we're basically going to say store OP. I believe we're going to say don't care, but here I think we're going to mention it in the subpass. Don't remember exactly, but we'll see later on. So here we create the render pass. We already created the layout, no? Weird, okay. So render pass info, all right, attachments, subpasses. And you can't just live with one subpass, but if you'd like, and in fact you could even create multiple render passes, I think, I guess, but you'd better off if you want more optimization in terms of tiling GPUs like Android, like phones in general. Basically, you'll probably want to deal with subpasses, but you can, in fact, especially in desktops, it doesn't really make a lot of difference. But yeah, it could be useful in some complex situations, but we're not going to be using those. Just going to have one subpass, and there you go. Create render pass, big success, and there you go. Nice. My brain hurts. Yeah, I feel like I've been trying to reach a singularity. This grinding sure hurts, but it's worth it for me, as I'm very determined to learn Vulkan, and I'm already starting to get the feel of the API and why many things are the way they are. This was 4 years ago. I wonder what I have done so far. That would be interesting. After about 2 days of trying to get my head around subpasses, render passes, attachment references, and attachment dependencies, it finally clicked. If someone doesn't understand, I suggest watching. Sure. If I understand it right, the reason for having an attachment reference bound to render pass and not to the subpass is to be able to declare an attachment once and reuse many times with respective attachment reference on subpasses, sharing the single attachment among many subpasses. Right, that is correct. It is also to verify though, to verify the validity, you know, like the pipeline wouldn't let you use an incompatible, non-incompatible render pass. So it makes sure to protect you also from ruin it up. So the naming invoker should be geared towards users of Vulkan rather than creator of graphics drivers. Should rather be named like before rendering, after rendering, and wiki clear attachment data and keep attachment data. That is very true. That is very true. That's much more intuitive name. Anyways, enough of comments now. Enough of comments. Let's see. Alright, so let's actually try to create a render pass. And this would actually be the final stage of creating the pipeline. And I think after that we'll probably end the live stream at that point. We'll see. We'll see how it goes. Anyways, what else? We'll see. Okay, let's go to create pipeline. Alright, let's add some other function pointers that we need right now. And look at that mountain. It, like, the name just gets bigger and bigger and bigger every time. So perfect. All right. All right, let's go. Now what we need, vk create render pass. And yeah, and then final, well, create render pass here too. Render pass. All right, nice. And now destroy render pass. Let's go. What is happening here? Am I doing something wrong there? Oh, yeah. Render pass apparently is like this. Interesting. Right, cool. Now I'd like to just order this for no reason before create graphics pipeline. All right, lovely. Now, but don't we actually need this swap chain? Oh yeah, I kind of messed it up, right? So we need the swap chain later on and the render pass to actually create the frame buffers, right? Yes. Now I remember. But yeah, it's not the thing that we need right now. Anyways, now what we need to do before this guy, let's actually create render pass. Well, device. Well, first of all, try map vkr device dot dispatches dot create render pass. And here we probably need the device as always, handle, and then, well, we need probably the info here, the render pass create info. And then here we probably need the, let's see, the probably the allocation callbacks null, and then finally it would give us the render pass. Yay. Cons, well, var render pass, it would be c.vk render pass equal and define. Let's go. And then we need the render pass info. C.render pass info, I guess. Oops. create info, right? And then the S type, as always, render pass, oopsies, create info. Then we need the attachment count, which right now we're just gonna have 1. And then we're gonna need the attachments. B attachments is equal to, well, I guess attachments, isn't it? It's actually called attachment description though. That would be better, I guess. Let's go. What else? There's dependency. We'll probably need dependency later on for synchronization, but for now we're not gonna use that, I think. I mean, aren't they using it here? Probably not, at least not now. Yeah, probably not. Cool. Okay, let's go back. What else? What other than that stuff? Flags. Subpasses, we're also gonna need that. I'm just gonna go with subpass, 1 subpass, and then p subpasses is equal to subpass, 1 subpass. That's all we really need now. Okay, great. Now we're gonna need the attachment description, which is gonna be called c.attachment description. And then I guess what? Right, final layout format. Well, let's start with the initial layout, I guess. c.vk, well, layout and defined. And that the final layout is equal to c.vk image layout present src, and then we have the format, which we should get from the swap chain. So maybe, ooh, interesting. All right, so I need the swap chain to actually get the format. Well, for now, I think I'm going to actually just, you know, let's see, just to hard code it. RG or what it was. Okay, let me see what I used. R8G8, there you go. That's the image format. I'm even hard coding it here, so that's not a big deal. Okay. There you go. Subpass, okay. So I'm just going to basically paste that there. Later on we can do something about that. Alright, other than that, what else there is? Initial layout, load OP. C.load OP clear, I guess. And then store OP equal to store, there you go. And then samples, count 1 bit. Do not have multi-sampling yet, and we do not have stencil stuff. But maybe we gotta still do it. Hold on, it really depends. Let me see. Attachment Lloyd, don't care. Let's see if that's 0. No, that's 2, so I gotta actually specify it. Cannot ignore that then. Interestingly, it's weird, but let's go. Okay, I think that's probably it. There's also flags, which would just be 0. And yeah, pretty much done. Done. Well, done with the attachment description. Okay. And finally, I think the subpass. Let's go. C.vacate. Well, subpass. Create info. No. What is it called then? Subpass description. Okay. Let's actually call this subpass description. Color attachment count 1. Color attachments. Interesting. It's attachment reference. Okay. Attachment reference. Calls attachment reference is equal to. By the way, you can get rid of the render buffer, the render pass, and I think also the frame buffers, maybe by using an extension called, I don't remember, I think direct drawing or something like that. No, I don't think. Dynamic drawing. Well, anyway, there is basically an extension, but it doesn't support currently, though. Of course, it's not in the core Vulkan. You have to make sure that the device that you're targeting actually supports it. That's the first thing. And the second thing, it doesn't support subpasses currently, although maybe there is plans to actually add that in the future. And subpasses are very useful for performance reasons for tiling GPUs, which are usually found on mobiles and maybe even laptops sometimes. So pretty much, because tiling GPUs are like, they conserve on energy pretty much. So, but yeah, either way. So let's say, for example, if you're targeting just desktop, then you probably would be fine without subpasses most of the time, unless if you're doing some weird crazy stuff. So anyways, attachment reference. Attachment reference, well, that's gonna be c.vk attachment reference. Let's go. Dot attachment 0. That's basically, as I said before, the actual location that you have set it in the fragment shader in out color, pretty much. And then the layout. What type is that? Image layout, isn't it? Yeah. So here it's basically would be color attachment optimal. I think that's probably it, because we gotta be using it to render into it. So I think that's pretty much it. Let's see, let me just go through it. Yeah, oh, I forgot this one. Pipeline bind point in subpass description, I guess. Oh yeah, I forgot about all of this. Alright, hold on. So there's color attachment count, which I already done, and there's color attachments already done. We don't need the input attachments. Depth, same thing. Stencil, we're not using that. Depth stencil would be useful for 3D later on, but right now we don't care. Pipeline bind point, this is important. And preserve attachments and resolve attachments probably would be useful for something like multi-sampling later on, I think, if I remember. So pipeline bind points. Well, vacate pipeline bind point graphics, and let's go. The other stuff, I'm just gonna use std.mem.0init. So it would initialize everything else to null or 0 depending on the type, basically the default value of the corresponding type. So here I'm actually going to, well, in fact, 0 init. And there you go. And basically this and this. Let's go. And that's pretty much, I believe, it. Do we need anything else here? No. Okay, did we create the render pass? I think so, yeah. And finally, I think for device.dispatch.destroy render pass. And here we gotta pass in the device as always, and then probably the render pass handle, and then finally the allocation callbacks. And there you go. I think for the render pass, there you go. Let us see if that actually works. I probably messed out some stuff. Let's see. Okay, dependencies. Oh yeah. Missing struct field. Now, since we're probably going to use dependencies in the near future, and I don't want to forget about that, I'm not going to use 0 init in this case. I'm just going to set it dependency count 0 p dependencies no. Alright, pretty much. And the flags, of course, is always 0. P next in render pass info. I'd like to do p next here, which is basically no. And let's see. And it seems to be compiling. Alright, nice. And our pretty much, yeah, we have made the render pass successfully without any validation errors so far. And here is all the API functions we're calling. Let's go, and as you can see, VK success for creating a render pass, creating pipeline layout, etc, etc. And then of course we also don't have any memory leak or memory, at least as apparent, and no leaked handles, at least in the happy path, which is basically in the success path. As I said before, I probably have to revisit off camera about the bad path, the sad path, which is about error handling. So anyways, who cares? So that's pretty much it for the render pass. Now finally we're ready to actually create the pipeline. And after that, we can basically create the frame buffers in the swap chain. And we're pretty much at that point done with all initialization. Unless if I forgot something. And then we're basically gonna need to go with, but of course, yeah, anyways. Frame buffers aren't a big deal. You just need the render pass and the swap chain, and it's kind of like just wrapper over the swap chain images, but then with the reference to the to the render pass. At least that's how I like to think about it. Some people may differ, but anyway. Structure type, and then graphics pipeline. Create info. Let's go. Now we just gotta basically use all of the infos that we have created earlier, pretty much. Pipeline handle, pipeline index, those are useless for now at least. Layout. Oh yeah, layout is equal to the pipeline layout that we have created. And what else? There is color blend state, which we have created also. Oh, and of course it should be an address, because those could be basically a lot, I guess. Right? What else? There's depth stencil state, which I don't care about, I think. Not sure, probably not. Dynamic state equal to dynamic state. Alright, what else? There is input assembly stage, which we have already done too. And oh, there should be an address of though. And what else? Multi-sample state. And then pnex, no, rasterization state. And then stages, which we have already done too. Although, do we have a slice here or an array? I think an array, so that, yeah, that's pretty good. Stage count is shader stages.len. And then what else? Tessellation states, we don't have that and we don't need it now. Vertex input states, yeah. There you go. What else? Viewport state? No, we don't need that since we have made it dynamic. So we're going to set that every frame basically, that's why. Viewport state, there's the render pass. And what else? Subpass. Oh yeah, select with subpass. Alright, it's 0 pretty much. So I could just basically ignore that. Alright, so that's pretty much it, I believe. Just gotta wrap this in a std mem0 init 0. Oh, std.mem.0 init. Kind of tortured name there for a second. Right, there you go. And I think that's probably it. But as always, let's not forget to actually clean up after ourselves. So device.dispatch.destroy graphics. Oops, destroy pipeline. And you'll notice here that when it comes to actually creating the pipelines, the creation function changes. But when it comes to destroying the pipeline and the handle itself, they're pretty much the same. Same as graphics, same as compute. And too simply just because they have, you know, different info structures basically. But yeah. So destroy pipeline. Now, pretty much as always, handle. And then here, I guess, yeah, we need the pipeline itself. And then we need the allocation callbacks probably. And we set that to no. By the way, let me turn on validation. And let's see what we have here. So, okay. Vertex input info. Oh, okay. Gotta make this an address of or pointer. What else? There's vacate pipeline, dynamic state, create info. Where's dynamic state? Oh yeah, here too. And it seems to be compiling now. And we got something about rasterization. Okay, let's see. So rasterization is enabled. But viewport state is equal null is not a valid pointer. The Vulkan spec states that the pipeline is being created with pre-rasterization shader state in the rasterizer. Okay, we gotta actually pass the viewport. But I don't think it matters. So we could just basically pass in some fake viewport dimensions since we're going to be setting that every frame anyways. That really doesn't matter, I think. Viewport state, I think. Oops, create info. Okay, let's see. S type is equal to C. There you go. And then flags, scissors, viewports. Okay, gotcha. Now for scissor count and viewport count equal 1, scissor count equal 1. Expect field initializer. Something is wrong here. What? C state. What? Expected field. Oh, yeah, I somehow forgot an equal there. Interesting. Okay, what else? There's just P viewports and P scissors. So viewport and then scissors equal scissor. As you can see here, you could probably set multiple ones, but you need the feature enabled. So in this case, we're just hard coding one viewport and one scissor. Right, what else? Yeah, that's pretty much it. Now, final thing, which is to simply give some junk data to viewport. So the validation doesn't bother us. Width, I don't know if I can set width to 0 though. I mean, let's see what's gonna happen if I do that. That would be interesting. Scissor, because as I said, it really doesn't matter since it is dynamic state. At least I guess so. Make scissor. Oh, what? What is the type of scissors? Yeah, it's VK-Rect 2D. Interesting. Oh, by the way, I forgot one thing. Minimum depth is 0. Although I don't think it matters again, as I said. But anyways. Alright, so scissor. Oh yeah, it's gotta be Rect 2D. Extent and offset. Now offset is to simply, I think X, yeah, 0, Y 0. Right. Extent is equal to, I would just set it to the viewport extent pretty much. Where is the width type? Oh, it's F32. And the scissor is U32. Interesting. I see. Cool. Oh well, just gotta hard code it honestly. Height, and we'll see what validation will tell us. So pretty much, I think that's it. Yeah. And that's, ladies and gentlemen, how you set a Rect 2D viewport. Oh, what? Oh yeah, see? Makes sense. Well. This is viewport state, so that makes sense. And let's go. Now we're just gonna make sure to set this on. Oops. There you go, P viewport state. Okay. Address of viewport state. And then, did I actually have to do anything else? Yes? No. I don't think, isn't it? Yeah. Yeah, it's hard in C to know if something is an array or, but it's probably not because there is no S here. So yeah, okay. Right, I think that's pretty much it. We need just flags here. And what else? Missing struct field P next. Here too. After this guy, null. And let's see if we get any validation error this time. Oh my. This is why validation is useful. Look at what I've done here. By mistake. Viewport state create info. You don't have this luxury on OpenGL and WebGL, especially WebGL, I think. Something like that. Just tells you invalid operation. Now figure it out. Rich. Zig build run. Oh yeah, the other nice thing about actually compiling your shaders yourself instead of compiling on the fly like OpenGL is that you just simply get no errors for actually compiling in runtime. Like you just remove that out of the equation. Okay, so I have another problem here. What is it? Must be... Did I mess it up again? Must be vacay. But what did I set it to? Vacay create graphics parameter. Viewport state type must be vacay structure type. Well, I guess let me make sure to copy it then. What happened there? And let me just make sure to copy it. What? Really? What the heck? Vacay pipeline viewport state create info. Parameter p create info 0 dot viewport state s type. So I have viewport state, which is this guy. S type must be vacay structures. Well, I have that. What? Like it's exactly that. Am I missing something or what? Oh, really? Now that error is gone. Oh, or maybe it was from before. Weird. But anyway, so right now we have finally created a pipeline. That was a lot of work. Now I think the next stage would be to just create frame buffers with the swap chain, and then we'll be done with the initialize. Well, in fact, I forgot about the command pool and the command buffer. But yeah, those aren't really big deal. Those are very simple, and also the fence distance. It never ends. Interesting. Is there any questions so far? Let me know. Alright, so we still have time to, I guess, to do the frame buffers.
Not longer.
And possibly to also do the... maybe the command pool and command buffers. They're pretty simple. Maybe even fences and stuff. But anyways, is there any questions so far? Let me know. Right, so far we got up to 828 lines of code. Alright, interesting. Alright, so I think I'm going to abstract this away. Maybe? Yeah. So let's actually create a pipeline. Alright. But one interesting thing is that Vulkan is pushing us towards creating multiple graphics pipelines at the same time. instead of doing one by one. Interesting. Okay, well, and in fact that function create graphics pipelines actually doesn't give us a graphics pipeline, it gives us just a normal pipeline. So that's interesting. Well, let's go to, I guess, device. FN create graphics pipelines. And let's go. Let's go. All right, what's going on here? This would basically give us a, well, I think an allocation, right? So cd.mem, we could optimize this a bit later on, but I don't care right now. Right, so what else? Well, let's see. Yeah, just slice, pretty much. It's gonna be a slice of c.vk pipelines. Too simply. Too simply. Now let's actually get the whole thing there. Let's see. In fact, honestly, I should start with the simpler stuff like, for example, render path. There is pipeline state, or sorry, pipeline layout. Okay, let's start with those because they're quite simple. Right, well, let's just copy this guy, I think. And let's go up there. Where is the device equals struct? Okay, well, fn, so we're gonna have like an fn create well, what is it? Pipeline layout. Alright, this is of course all subject to change. Pipeline layout. And here basically self.dispatch. Factory function. Self.handle, here layout info. Layout info would basically be c.vk layout create info. Let's go, and honestly let's just call it info. Oops. And there you go. Now the third device.dispatch. Well, self there. .dispatch. Self.handle. And well, this is gonna be the error defer. And well, the other guy would be on another place. Well, in fact, it won't give us this. It would give us a pipeline layout. Just like that. Construct pipeline layout, isn't it? Oh, what I'm doing here. Let's use our beautiful thing that we have made before, class, and there you go. You just call this pipeline layout, and let's go. And now, oh yeah, I forgot about some things that we could do too to make this faster. Okay, let's create another one. So basically it's usually kind of like this, where you don't have an init function, but you have a handle, and that handle is kind of like c dot. Well, here that changes, so let's say vk pipeline create info. Like for example here, let's say pipeline layout. So it's basically create, where is the info? Yeah, it's right here. So it's basically vacay create info. Okay, so here what we could say 0 and then create info. Oh, but what's happening there? Yeah, it's fine. And what else? Basically we could say allocation callbacks and then c dot vacay allocation callbacks. This is gonna make it much easier for us to do wrappers like this. Vacay allocation callbacks, cool. And then the init is, well, usually here you have device basically, and then here you have self.device. Oops, why it's not doing it right? Anyways, self.device.dispatch, you usually have that, and then you basically say vacay, oops, actually say destroy, and then here basically the name, which is that guy. So for example here it's called destroy pipeline layout, and then here you say self.handle, same thing, and then here you say self.device.handle, and then self.handle, right? Comma null. And in fact I'd like to call this just handle, by the way, just to keep the terminology the same, be consistent. And yeah, pretty much destroy, for example, destroy pipeline layout, vacay pipeline layout create info, pipeline layout, self.device handle. Oh, and instead of null here it should be self.allocation callbacks. And let's go. Alright, so this would make our job much easier. I'm gonna call this vacay class, I guess. Alright, let's say Control-Shift-B, create code snippet, zig, enter snippet name. I'm going to call this, I guess, vacay class. And then here, let's say vacay class, enter snippet description, vacay class. And now, here's what I can do. Vacay class, and then I could say, for example, in our case, it's pipeline layout and magic. And there you go, done. Isn't that so cool? Nice. Nice. Oh, I actually done something wrong here. Yeah, my bad. Go back. Yeah, I done. So here it should be just vacay, not create info, just vacay. Yeah, pretty much. So my bad. Right. Is that right now? Yeah, I think so. And yeah, let's now do Control-Shift-B, create code snippet, zig, enter snippet name, vacay, I guess, class. And now here, just call it vacay class, enter snippet description, vacay class. And there you go. Now let's try again. Vacay class, pipe, what? Why? Hold on. In fact, let's go back before. And now let me actually go to code snippets. Or snippets. Configure user snippets. Existing snippets. Okay, let's remove this stuff first. I'm going to keep zig struct, but vacay class, let's remove those. Alright, now hopefully it won't be confused this time. So Control-Shift-P, create code snippet, zig, vacay class, and then alright, hopefully now it works. What? Really? What the? Configure user snippets. Why didn't I add it? Stupid stuff. Really? Okay, hold on. Let me try it again. This is so weird. Create code snippet. Zig. Enter snippet name. I'm gonna call it Vicky handle. Change the name. Snippet prefix. Vulkan handle. Wrapper. What? This is so stupid. Why? Let me actually rerun this. Where we was ZigVK? Okay, let me try again now. Come on, ZigJSON. Oh no, not this. Let's go. Control Shift P. Create code snippet. Zig. Enter snippet name. Vk handle, I guess. Vk handle. Snippet description, Vulkan handle wrapper. Really? This is so stupid. Let's see. Well, I guess we gotta do it manually because this is so bad. Plugin is broken, I guess. Alright, let's try to do this. So, Zig. Actually, not Zig. Vk handle, right? Alright, now prefix. Prefix is Vk handle. Now let's say body. And the problem with doing it the manual way, as you can see, is that you have to actually do that yourself. And then there's also description, which I don't care about. But let's just say Vulkan handle, wrapper, or whatever. Alright. Now I gotta figure out how to actually make this stupid thing into JSON. Bruh. Gotta manually do this? Really? Really? Oopsies. This is so stupid. And then for a new line, you have to do it like this. Come on, are you kidding? Well. Instead of writing actual code, just fighting with the stupid IDE. Well. Is that the case? think so. Okay, now we gotta figure out to make sure that the tabs are right. This is so stupid, but anyways, hopefully now that works. Now control, well, actually vacate handle. Now let's say you say pipeline layout, and there you go. Oh, I just need a comma there, here. That's pretty much it, I guess. Now let's go again, vacate handle, pipeline layout. I wonder how much time. Okay, and there you go. And I guess that's it, hopefully. As you can see, everything is done already. Lovely. Nice, nice, nice. Very, very nice. Okay, create pipeline layout, destroy pipeline. I think we could probably also do the same exact thing with this guy, with this kind of create functions. But it's very time consuming. Oh well. Okay, I guess. Let's try. Okay, so here, now the problem is that I'm not naming my functions. Yeah, well, pipeline layout. Okay, I think I just gotta have. There is a way though using, but I don't really remember how to make it snake case once again. But anyways, so just gotta do it manually now. Well, how do you do it again? Okay, let's see. So you create something, and then again here, you gotta change this to, let's say, 1. Same thing here. Create. Same thing here. And there you go. So yeah, I think that's pretty much it. Oh, here too. And that's pretty much it, I think so. Alright, lovely. Now let's just go ahead and say, let's see, other than that. Oh, where's the allocation callbacks? Oopsies, I forgot about that. Well, let's actually add the allocation callbacks. I forgot. There you go. Just gotta add these guys. Pretty much. Just gotta add them here. And then instead of null, say this. And oh, I forgot to return. Oh yeah, well, that's crazy. Well, here we just say device, oopsies, dot device is equal self, and then dot handle is equal handle, and then the allocation callbacks is equal to allocation callbacks. And let's go. Right, so I think pretty much that's it. Hopefully, yes. Yes. So now let's just do this. And although in this case the error defer isn't really needed here, but you never know. when we could add something there for whichever reason. So return, it's just a good practice to always do that. Okay, cool. Okay, let me see what I'm doing here. Allocation callbacks, and let's go. All right, I think I'm doing it right now. Now I gotta basically turn that, but let's try again with using that plugin. Hopefully now it works. So stupid. Create code snippet zig, and then the snippet name, let's say vk handle factory or vkc handle, vk create, and here vkc, I guess. And then enter snippet description, whatever. And bruh, like literally. Well, that's so stupid. Where is it? Is there another? Let me try to find something else, I guess. Is that just so bad? Alright, well. It is so stupid. Oh, well. Let's try this one, hopefully. Name. Handle, I guess. Or vk handle creator. And then trigger. What is trigger? I think they mean the prefix. So I guess vkc create handle. Alright, description, blah blah blah, I don't care. Why are you even talking about? Like, bruh. I mean, come on, do I have to actually make my own extension now or what? This is so weird. I would have better just created a Python script instead of trying this. Custom snippet maker. What? Markdown snippets? Bruh. Okay. Okay, let me try this one. Hopefully this would work. I'm so tired of this stupidity. Create snippet. Enter snippet name. vk handle creator. Custom prefix. vkc handle. Enter snippet scope zig. Oops. zig. Apply variables default false. What do you mean by apply variables? I guess true. Okay, let's say for example, pipeline layout. Okay, I think that worked, finally. Okay, so yeah, I think that worked. Yep. Alright, finally. So I guess let me try to maybe give you the link to that, so you do not have to go crazy with it too. Alright, let's go. Here's the extension. Not sure if it would work later on though, but we'll see how it goes nonetheless, hopefully. But at least right now it worked. Finally, something that works. Okay, great. So now, I guess we can go back to the actual code. I don't have a lot of time left, but let's see. Create pipeline layout. Great. Then it returns that guy. Alright, lovely. Now let me actually try to use that. And I'm really glad that I used this first on simple object as a pipeline layout for now. Although it's gonna be hairy later on, but right now it is simple. So, okay, where is it? Where are the stupid stuff we have created? Yeah, here, there you go. Okay, let's just create it here. So let's say const pipeline is equal to device or create pipeline layout, and then here you give it the info. Ooh, okay. So you can, I guess, do this. Then allocation callbacks null. And yeah, can I do that now? Oh man. ZLS, what is going on? Just what is going on? Pipeline layout. Okay. And yeah, ZLS is not wanting to help at all. Amazing. C.vacate pipeline layout info. Well, there you go. This type is equal to C dot structure type. Well, okay. Pipeline. Oops. Create info. Oh, pipeline layout. There you go, and that's pretty much it. But well, we gotta actually use that std.mem. Now I don't know if I'd like to actually use that guy in here, or let's see. I mean, I guess, yeah, we can maybe do that. Like, basically what I'm talking about here, what I'm thinking is that maybe you could, instead of this, I mean, ZLS is not helping anyways, so instead of that, you could say maybe any type. I think now instead of doing that, I don't know what to call it now. Const, oops, I guess create info. Okay, is equal to, let's say, std.mem.0 init. Ooh, comp time t type. Now here you basically say vk dot, well, what I'm doing, c.vk pipeline layout, and then the init is basically info in this case. And of course here, instead now of using that, I can just say create info. And yeah, we could basically like embed that into there, and that maybe would be nice. So right now I don't have to always say cdmem0. Where's that stupid thing? There you go, okay. So now I could basically say this, and I guess that could work. Defer the init, and there you go. Let's see if that actually works. Well, there you go. Cannot cast into pointer type child. What? c.vk pipeline layout. Pipeline layout t. Expected type found pipeline. What? So in fact this gives us a type. Interesting. What? Oh, never mind. Expected type. Dot home code otaku. Oh. CVK pipeline layout. Okay. Okay, where I'm actually doing that. Pipeline layout. VK structure type pipeline layout. Create info. CVK pipeline layout. Handle. Very weird. Right. Found VK pipeline layout T. Oh. My bad. Oh my god. That is just so stupid. Well. Oh well. Very weird stuff. Alright. Okay, what else? Main pipeline. Oh, I think I know. Let's see. Expected. Oh yeah. Forgot about the error. What else? No field remember function named the init in. Well, try. Expected type found main pipeline layout. Oh, let me go back to the thing. Maybe we have a problem in the init. Okay. All right. Well, that should work. Expected type found main pipeline layout. But where? That is weird. Okay, so I'm sure that it's here now. Okay, let's try to figure it out. Let's see. All right. Expected type. Oh. Amazing how you can sit down and code for 5 hours straight. Yeah, that's normal. Well, create info. I don't know when Zig will fix this stupid thing. Like it shows you the whole stupid path. Like what? Just show me the stupid last thing. So it expected a vacate pipeline layout, but it found pipeline layout. What? What in the world? It's probably some stupid thing that I can't see. Well, this is another level. Oh well. Allocation callbacks, pipeline. So we got the vacate pipeline layout here. Create info is equals 0 init. Vacate pipeline layout create info, and there you go. That's the info. Now create pipeline layout self.handle, which is pretty much the device handle. Then we got the address of the create info. Okay. Then allocation callbacks, and then an address to the handle. Okay. And then dispatch, destroy, pipeline layout, set handle, allocation callbacks, and then we're returning this stupid thing. What? There's just nothing wrong with that. Oh my god. Well, the problem wasn't there, I think. The problem is in here. Well, that's so stupid. And of course we gotta add in an address there. And cast discard cost qualifier. What? I think it should be var for some whatever reason. What? Cannot cast. So expected type struct vk pipeline layout t. Oh, maybe we don't need that. What about now? Let's see. And finally, well. So I think I'm probably gonna end it here. Yep, pretty much. But pretty much right now, I think it would be easier to add that stuff, the other stuff, to abstract the other stuff basically, because right now we know how to create snippets, and we already have this guy. So you could just make a snippet out of this and then basically proceed with the other stuff. Oh well. That was quite crazy. And there you go. So that was it for this live stream. And is there any questions before we end? And of course I'm going to go ahead and what is this? Oh nice. So this actual extension adds the snippets in the repo itself, which is nice because now anyone who cloned the repo with VS Code will have the same snippets. Amazing. That is very useful. Okay. Great. Shader.frag main.zig. So we basically didn't do much, I think. No. Well, we have done much. Well, we created the pipeline. That was a lot of work, I think. There you go. Bruh. Okay, so pipeline done. Graphics pipeline. And yeah, pretty much. Now shader.frag.spv, Vertex SPIR-V. One last thing before we're done here. I'm just gonna copy the commands of compiling the shaders. Oh my god, come on. There you go. Okay, I'm just gonna copy these commands. Gonna put them into a script. Oops. And then I guess I'm gonna put it in maybe dev assets. No, let's just put it here. Let's call this compile shaders.sh. and there you go. But let's see. Let's just do this, and now it's the vert becomes frag, and now I could just simply say how to do that. Well, chmod plus x compile shaders .sh, or too simply we could just say sh compile shaders.sh, and there you go. Lovely, lovely, lovely. And that's pretty much it. Now if you do not have these, which move to trash, and then you do this, and there you go, it just compiles it on the fly. Let me make sure everything still works just as fine. Yep, it does. Amazing. So one last thing I'm going to do, which is to create a folder called shaders. Pretty much, in fact, I'm going to do it here, and you'll know in a second why. So mkdir well, src/assets/shaders, and then I'm basically going to add shaders here. And yeah, now I'm just gonna make sure to delete this stuff that is already here. And now when you compile that guy, it brings in a shaders folder, and it contains the compilations. Interesting. Now just gotta do one final change, which is to change the path. So frag.sp, there you go. Oops, just gotta make sure to add /shaders here, and same thing with this guy, and now it should still work just as fine. And yeah, it works. Lovely. So now I think I'm done at this point. I just gotta add one thing in getIgnore. I'm gonna add src/assets/shaders. There is no need to to add the compiled shaders to the version control. It's gonna be annoying. So yeah, basically anyone could just go ahead, compile the shaders, and there you go, and just run the build. Alright, after 23 minutes. Okay, so that's pretty much it. Now I'm just going to add everything that we have here, and I'm going to commit. And by the way, I think we could probably do the same thing with Windows, but since I cannot try, I'm just not gonna add it. So if anyone is on Windows, try to make that script .bat file basically. Now let's just sync the changes. Come on. Really? That's so stupid. github.com, let's see if it's got pushed. And zigvk or vkzig. Vkzig. Zigvk, okay. Let's go. And yeah, the change is live, finally. Alright, so yeah, pretty much that was it for this live stream. That was a big one. And yeah, see you later. Goodbye everyone. Thank you for tuning in. Thank you for supporting. And have a great day or a great night. So yeah, goodbye.